For thousands of years, the smartest people alive looked at sleep and basically saw a switched off light. The ancient Greeks personified sleep as a god called Hypnos, and they made him the brother of Thanatos, who was the god of death, which tells you exactly how they thought about it. Sleep was a little rehearsal for dying. You stopped taking in the world, you went still, the lights went out, and then in the morning the lights came back on. There was nothing to study because, as far as anyone could tell, nothing was happening. That view held up for a shockingly long time. Even into the early 20th century, the standard scientific opinion was that the brain fell asleep because it ran out of things to do. The idea was that during the day, your senses kept pouring information in, sights and sounds and touch, and that flood of input was what kept you awake. So when night came and the input dried up, the brain simply powered down on its own, the way a machine idles when you stop feeding it work. Sleep was passive. It was an absence. It was what was left over when waking stopped. The first crack in that idea did not come from a sleep lab, because there were no sleep labs. It came from a plague. During and just after the First World War, a strange illness spread across Europe and then the rest of the world, and it did something to people that nobody could explain. Some of the people who caught it fell asleep and could not be fully woken, drifting in a heavy stupor for days, weeks, sometimes years. Others got the opposite and could not sleep at all, lying awake night after night until they were wrecked. The disease killed a huge share of the people it touched, and the survivors were often left frozen and slowed for the rest of their lives. A Vienna doctor named Konstantin von Economo started studying the brains of the people who died from it, and in 1917 he gave this new disease a name, encephalitis lethargica, which roughly means an inflammation of the brain that makes you sleepy. But the thing that mattered for the science of sleep was what he noticed when he compared the two kinds of patients. The ones who could not stop sleeping had damage in one specific part of the brain, near the base, in a region called the hypothalamus, and the area around it. And the ones who could not sleep at all had damage in a different part, just in front of the first. This was the clue that changed everything, even though it took decades for people to fully believe it. If destroying one small patch of brain tissue could force someone into endless sleep, and destroying a nearby patch could rip sleep away entirely, then sleep could not be a passive switching off. There had to be machinery in there. There had to be an active system, an on switch and an off switch built right into the brain, deliberately putting you to sleep and deliberately waking you up. Von Economo had basically predicted, from looking at damaged brains, that the brain contains a dedicated sleep control center. He was nominated for the Nobel Prize 3 separate times, and he was right, although it would be most of a century before anyone could prove the details. There is a haunting tale to the story of that sleepy plague, too. Many of the people who survived it did not recover into normal lives. They were left frozen, slowed almost to statues, conscious inside, but barely able to move or speak, in some cases for decades. In the late 1960s, a neurologist named Oliver Sacks tried giving some of these long frozen survivors a then new drug, and for a brief, astonishing window, a number of them woke back up, moving and talking again after years locked inside, before the effect faded and most of them slipped back. Sachs wrote about it in a book called Awakenings, which was later made into a well-known film, and it stands as one of the strangest chapters in the whole history of sleep and the brain, an epidemic that put people to sleep for 30 years, and a drug that briefly woke them. Around the same time, another piece of the puzzle arrived from a German psychiatrist named Hans Berger, who in 1924 did something that sounds almost impossible for the time. He found a way to record the electrical activity of a living human brain from outside the skull by placing sensors on the scalp and reading the tiny voltage changes underneath. This was the birth of the electroencephalogram, the EEG, the squiggly line readout you have seen in every hospital drama. Berger was a quiet, somewhat obsessive man, and a lot of his colleagues thought he was a crank, but he had handed sleep science the one tool it absolutely needed. For the first time, you could watch what the brain was doing while a person slept without waking them up to ask. Berger's reason for hunting brain waves in the first place is one of the odder stories in science. As a young man, he had a brush with what he became convinced was telepathy, an experience that made him believe the mind might give off some kind of physical energy that could pass between people, and he spent years trying to find that energy. He never found telepathy, of course, but in chasing it, he stumbled onto the real electrical signals of the brain instead. For years, his work was ignored or dismissed by the scientific establishment, and only late in his life did the rest of the world catch up and realize he had been right about the brain's electricity all along. He did not get to enjoy the vindication for long, and the story of his final years is a sad one. But the tool he invented, chasing a phantom, became the foundation that the whole study of sleep was built on. And once people started looking with that tool, they found something nobody expected. The sleeping brain was not quiet. It was not a flat line. It was producing big, slow, rolling waves of electrical activity, very different from the fast, small ripples of a waking brain, but unmistakably busy. The brain at night was doing something. The only question was what? The man who turned that question into an actual science was a Russian immigrant named Nathaniel Kleitman, who set up the world's first dedicated sleep laboratory at the University of Chicago in the 1920s. The cot his subjects slept on sat under a metal hood that had originally been built to suck dangerous fumes out of the lab, which gives you a sense of how seriously the rest of the university took the topic. Kleitman did not care. He became obsessed with the basic rhythms of rest and activity in the body, and he was the kind of scientist who used himself as the experiment to test how the body handled going without sleep. He once stayed awake for 180 hours straight, which is about a week, just to record what happened to his own mind and body as it fell apart. His most famous stunt was in 1938 when he and a research partner went down into Mammoth Cave in Kentucky and lived there for more than a month, deep underground, where there was no daylight and no normal sense of time. They were testing whether the human body could be forced onto a longer day than the usual 24 hours, and they tried to live on a 28-hour schedule. That cave experiment, weird as it was some of the earliest serious work on the body's internal clock. And we are going to come back to that clock in a big way because it is half of the entire explanation for why you sleep when you sleep. Kleitman wrote the definitive early textbook on the subject called Sleep and Wakefulness in 1939, and he is often called the father of modern sleep research. Gleitman also made a quieter discovery back in the 1930s that turned out to matter enormously, which is that even a perfectly well-rested person is not equally sharp all day long. He found that our speed and accuracy at mental tasks rises and falls on a daily rhythm, dipping in the very early morning hours and dipping again in the early afternoon, regardless of how much sleep we got. In other words, your brain has good hours and bad hours baked into the day itself. And that built-in afternoon dip is the real biological root of the slump you feel after lunch, long before you ever blame the sandwich. That single observation, that performance itself, runs on a clock, is one we will see come back to bite people in some of the worst disasters of the 20th century. But Kleitman's biggest contribution was not anything he did himself. It was a broke, stubborn graduate student who knocked on his office door looking for a project and who would go on to discover the single most important fact about sleep in the entire 20th century, mostly by refusing to believe his equipment was broken. His name was Eugene Aserinsky, and in 1951, he was about as far from a celebrated scientist as you can get. He had grown up poor in Brooklyn. His mother had died when he was 12, and his father was a dentist who loved to gamble so much that he would sometimes pull his young son in to fill an empty seat at a card game. Eugene had bounced around for years, taking college courses without ever finishing a degree, enrolling in dental school and discovering he hated teeth, keeping the books for an ice company, working as a social worker, and doing a stretch in the army, handling high explosives, even though he was legally blind in one eye. By the time he talked his way into the University of Chicago as a graduate student, he had a wife, a young son, a second child on the way, and almost no money at all. At one point, things were so tight that Gleitman, his supervisor, loaned him $100 and suggested he save money by eating chicken necks. Gleitman gave him a project that even Aserinsky later described as about as exciting as warm milk. The job was to sit and watch the eyelids of sleeping babies and write down what they did. Sleep was the least interesting field Aserinsky could imagine working in, but he needed the work, so he did it, sitting by cribs for hours. Eventually, he moved on from infants to adults, and he made a decision that, at the time, seemed almost wasteful. He decided to run a brainwave machine all night long continuously, recording the sleeping brain from the moment a person dozed off until morning. Nobody really did this because everyone already knew sleep was a flat, featureless thing. So why burn through thousands of feet of expensive graph paper, recording a whole night of nothing? The machine he used was an old, second-hand brainwave recorder called an Offner Dynograph, which he had dragged up from a basement and tinkered with until he half trusted it. On a December night in 1951, his 8-year-old son, Armand, was the test subject. Aserinsky scrubbed the boy's scalp and the skin around his eyes, taped on the electrodes, plugged the leads into a box over the bed, and settled in for a long night watching ink pens scratch lines across a slowly unrolling banner of paper. And at some point in the dark, the pens did something they were not supposed to do. The pens tracking the boy's eye movements suddenly started swinging back and forth, sharp and active, the exact pattern you would expect from someone who was wide awake and looking around the room. The brainwave pens jumped too. So Aserinsky got up and went into the room to check on his son, fully expecting to find him lying there, awake with his eyes open. But the boy was sound asleep, eyes shut, completely out, while the machine in the other room insisted his eyes were darting around like a person watching a tennis match. Now, the easy thing to assume here is that the machine was broken, and Aserinsky's whole career almost died on exactly that assumption, because, for a while, he could not be sure the old dynograph was not just inventing the signal. He worried the machine might be picking up activity from the muscles of the inner ear instead of the eyes. He worried his subjects might be briefly waking up without opening their eyes. So he did the only thing that could settle it. In one of the early sessions, while the pens were doing their strange dance, he quietly opened the door to the dark room and looked directly at the sleeping person's eyes through their closed lids. And the eyes were moving vigorously, while the person did not respond to his voice at all. There was no doubt left. The subject was deeply asleep, and the eyes were going wild. By his own account, by the spring of 1952, he was certain he had found something real and unknown. He ran more than 50 all-night sessions on roughly 24 people, and the same thing showed up again and again. There were these recurring periods, several times a night, where a sleeping person's eyes raced back and forth. Their heart sped up, their breathing got faster and more irregular, and their brain produced waves that looked almost exactly like the waves of a waking brain. He thought about naming it jerky eye movements, but he decided against it because he did not want critics latching onto the word jerk to mock his findings. The phenomenon got a calmer name, rapid eye movement, REM. Then came the part that turned a curiosity into a revolution. Aserinsky started waking people up during these eye movement periods and asking them what had just been going through their heads. And over, the answer was that they had been dreaming with vivid, moving, visual scenes. Wake someone during the quiet, slow-wave parts of the night, and they usually had little or nothing to report. waked them during a burst of rapid eye movements, and they were in the middle of a dream. The eye movements and dreaming were linked. The brain, far from being switched off, was running a private cinema at scheduled times all night long. There is a small story from this period that captures how stubborn and curious he was. He wondered whether the moving eyes were literally watching the dream play out, so he talked the blind student into spending the night in the lab to see whether a blind person showed the same eye movements. The student brought along his guide dog. Late in the night, when the eye channels started getting active, Aserinsky carefully cracked open the door to the dark room to look at the sleeping man's eyes, and a low growl came out of the darkness. Because he had completely forgotten about the dog, he shut the door and gave up on that particular experiment for the night. In September of 1953, Aserinsky and Kleitman published their findings in the journal Science. The paper was barely 2 pages long, and it landed quietly, but it cracked the whole field open. As one history of the discovery put it, REM was less important for what it revealed than for what it began. It proved that sleep was not one single state. It proved the brain cycled every night between completely different modes of operation, and that one of those modes was nearly as active as being awake. The continent of the sleeping brain had finally been spotted, and now people could start mapping it. One of the people Kleitman assigned to help with the overnight studies was a medical student named William Dement, who would go on to become one of the giants of the field and basically the founder of sleep medicine as a discipline. Dement later described the moment Aserinsky told him the eye movements might be tied to dreaming as more thrilling than being handed a winning lottery ticket. There is a detail here that is almost funny in hindsight, which is that Kleitman had banned women from being sleep study subjects because he was afraid of scandal, and the men had to specially talk his way into wiring up his own girlfriend with the condition that Aserinsky stay in the room as a chaperone. One of the other early female subjects Dement recruited was a University of Chicago student named Elaine May, who a few years later became famous as half of the comedy duo Nichols and May and went on to write Hollywood movies, which means she has a strange little footnote in the history of sleep science. Dement and Kleitman then did the careful work that nailed the dream connection down for good. They woke sleepers up hundreds of times across many nights, sometimes during rapid eye movement sleep, and sometimes during the quiet stages, and they kept score. When they woke people out of REM, those people reported a vivid dream the large majority of the time, something like 4 out of 5 awakenings. When they woke people out of the deep, quiet stages, dream reports were far rarer and far thinner. That lopsided result was the proof. Dreaming was not scattered randomly through the night. It was concentrated in this one specific electrically active state. Dement went on to map out the full repeating structure of a night of sleep, the regular cycling between the stages, and decades later, he opened one of the first clinics devoted to sleep disorders and helped turn the study of sleep into a genuine branch of medicine. The thing Aserinsky spotted in a basement with a broken-looking machine had grown into an entire science. A few years later, a French scientist named Michel Jouvet pushed the discovery even further. He realized that this REM state was not just a lighter or shallower version of normal sleep. It was a genuinely separate third state of being, as different from ordinary sleep as ordinary sleep is from being awake. He gave it a name that stuck, paradoxical sleep, because of the contradiction sitting at the heart of it. During REM, your brain is roaring with activity, almost as if you were awake, and yet your body is essentially paralyzed, your muscles switched off so you cannot move. Jouvet figured out which part of the brainstem produces that paralysis, and he proved it by lesioning that exact spot in cats. The cats, freed from the paralysis but still in REM sleep, would get up and act out their dreams, raising their heads, arching their backs, stalking and pouncing at things that were not there, all while completely asleep. That detail is going to matter much later because in some people, that paralysis switch fails in real life. But hold on to it for now. As for Aserinsky himself, the story does not have the tidy ending you would hope for. After the discovery, he walked away from sleep research almost entirely, partly out of his own difficult, suspicious personality, and partly because his life kept getting harder. He spent a year studying the effects of electric currents on Salman, his first wife, who struggled for years with severe depression, died by suicide in 1957. He had long stretches where he was not in contact with his own son. For years, the wider sleep research community basically forgot he was alive, and at one conference, people who saw his name tag reportedly said they had thought he was dead. The thing that pulled him back into the light was almost absurd. In 1989, a sleep researcher had a custom license plate that read REMSLEP. And one day, in a store parking lot, a woman walked up and told him she loved the plate because her father had discovered REM sleep. It was Aserinsky's daughter. That chance run-in eventually led to Aserinsky being invited to address a huge sleep conference, where he got a standing ovation from a ballroom of scientists, many of whom had only ever known him as a name on a famous paper. People stopped him to point and say, "There is Aserinsky." A few years later, in 1998, he was driving in California when his car ran off the road and hit a tree, and he was killed. The autopsy could not say why it happened, and no other car was involved. It is entirely possible that the man who discovered the science of sleep died because he fell asleep at the wheel. So if sleep is not one thing, what is it exactly? When you fall asleep tonight, you are going to move through 4 distinct stages, and you are going to cycle through them over and over until morning. 3 of those stages are grouped together as non-REM sleep, named N1, N2, and N3, and the 4th is REM, the one Aserinsky found. Think of it less like a single off switch and more like your brain walking through 4 different rooms in a set order, again and again, all night. The way scientists tell these stages apart is by reading your brain waves, and the pattern is genuinely beautiful once you see it. When you are wide awake and focused, your brain produces fast, small, busy waves, all your neurons firing out of step with each other as they handle 1,000 different things. When you close your eyes and relax, those speed up patterns give way to a slower, more even rhythm. As you drift into the lightest sleep, the waves slow further. And as you sink down toward deep sleep, more and more of your neurons start firing together in unison, producing those huge, slow, rolling delta waves, the signature of the deepest sleep, where the whole brain is pulsing in synchronized swells. Then in REM, the readout suddenly looks almost like waking again, fast and busy, which is the paradox that gave the field its first great mystery. The entire architecture of a night is really just the brain shifting between these electrical climates over and over, and the sleep spindles and other little signatures embedded in them are the brain quietly doing specific jobs at specific moments. The first room is N1, and it is barely sleep at all. It is adrift, the in between state in the first few minutes after you close your eyes. When your muscles start to relax, your brain waves slow down, and your eyes roll gently under the lids. It is so light that if someone woke you up out of N1, you would probably swear you were never asleep in the first place. This is also the stage where you sometimes get that sudden falling sensation followed by a full body twitch that jolts you awake, which has a name, the hypnic jerk, and which is extremely common and basically harmless, even though nobody is completely sure why it happens. From there, you sink into N2, which is where you actually spend most of your night. For a healthy adult, this single stage takes up around half of all the time you are asleep. On a brainwave readout, N2 is where two strange little signatures show up. One is the sleep spindle, a quick half-second burst of fast brain waves, and the other is the K complex, a single big sharp spike. These are not random noise. They are the brain doing work, and the sleep spindles in particular are going to turn out to be deeply involved in locking in your memories, which is a thread we will pull on later. During N2, your body temperature drops, your heart rate slows, and the outside world starts to fade further away. Then comes the deep one, N3, also called slow wave sleep or deep sleep. This is the bottom of the pool. Your brain waves here stretch out into huge, slow, rolling waves called delta waves, all the neurons firing together in long, synchronized swells, which is about as far from waking brain activity as you can get. This is the stage where you are genuinely hard to wake up, and if someone does drag you out of it, you come up groggy, confused, and disoriented for a few minutes, which is that horrible feeling of being woken from the deepest part of a nap. N3 is when your body does most of its physical repair work. The vast majority of your growth hormone gets released during this stage, which is part of why children who are busy building entire bodies spend much more of their night down in deep sleep than adults do. And then, after you have gone down through these stages, Your brain does something that, before a Serinsky, would have made no sense at all. Instead of just staying down in the deep, it climbs back up and crosses into REM, the fourth room where the paradox lives. Your brain lights up almost as if you were awake. Your eyes start their rapid darting, and at the same time, your body goes limp, your major muscles switched off and paralyzed, so that whatever your roaring brain is doing, your body cannot act on it. This is the room where the vivid story like dreams happen. It is also, in a sense, the most dangerous looking state in all of biology, a fully active brain trapped in a fully paralyzed body every single night. That whole trip down through the light stages, into the deep and up into REM makes one sleep cycle, and a single cycle takes roughly 90 minutes, though it can run anywhere from about 80 minutes to 2 hours. You do not just do this once. A normal adult runs through 4 to 6 of these cycles a night, one after another, which is the actual reason the standard advice lands around 7 to 9 hours, because that is how long it takes to get a full set of cycles in. But the cycles are not identical copies, and this is the part most people never learn. The mix changes as the night goes on. In the first half of the night, your cycles are loaded with deep N3 sleep, all that slow wave physical repair, with only short little bursts of REM. As the night goes on, that flips. The deep sleep shrinks, sometimes vanishing completely by the early morning, and the REM periods stretch out longer and longer. Your first REM period of the night might last only a few minutes, while your last one just before you wake up can run for the better part of an hour. This has a real consequence for your life. It means the front of your night is mostly about deep, restorative, body repairing sleep, and the back of your night is mostly about REM, the dreaming, memory, and emotion processing sleep. So, if you regularly cut your sleep short by waking up early, you are not trimming a little bit off the end of something uniform. You are specifically slicing off most of your REM, the part that handles memory and mood, while keeping the deep sleep at the start. And if you stay up too late, you eat into the deep sleep at the front instead. The two halves of your night are doing genuinely different jobs, and cutting either end costs you something specific. There is also a clue hiding in how this changes across a lifetime. A newborn baby spends around half of its total sleep in REM, sometimes 8 hours a day of it, far more than any adult, which is one of the reasons scientists suspect REM is doing something important for building and wiring a brain, not just running dream. As you age, the amount of deep, slow wave sleep you get tends to drop, which may be part of why older adults often sleep more lightly and wake more easily. The shape of your sleep is not fixed. It changes as your brain changes. So that is the what. Every night you run this hidden, structured program, cycling between physical repair and brain activity in a pattern your conscious mind never sees. Which leaves the much harder question: what decides when this whole program switches on in the first place? Why do you get sleepy at night and wake up in the morning instead of just falling asleep at random. And the answer to that is not one system, it is two, running at the same time, and they are worth understanding on their own. The best way to understand why you sleep when you sleep is an idea scientists call the two-process model. And the name sounds complicated, but the idea is simple. Two completely separate systems are pushing on you at all times, and your sleepiness at any given moment is just the sum of the two. The first system is a clock that tracks the time of day and tries to keep you on a roughly 24-hour schedule no matter what. The second system is more like a pressure gauge that fills up the longer you are awake and drains while you sleep. The clock decides when it should be night. The pressure decides how badly you need sleep. When the two line up, you sleep well. When they fight, you get jet lag, or you lie awake at 3 in the morning, wired and exhausted at the same time. Let us take the clock first. You have buried in your brain a master clock. This is not a metaphor. There is a physical clock in there, a tiny clump of cells, and it runs on a cycle very close to 24 hours, all on its own, even with no information from the outside world. We call the rhythm it produces your circadian rhythm, from the Latin for roughly a day, and it governs far more than sleep. It sets the daily rise and fall of your body temperature, your hormone levels, your alertness, your digestion, even the timing of when you are most likely to have a heart attack. The first proof that this clock exists at all came in 1729, which is wildly early, and it came from watching a plant. A French astronomer named Jean-Jacques de Miran had a mimosa plant on his desk, and he had noticed that it opened its leaves during the day and folded them up at night, like most plants tracking the sun. So he did the simple, obvious experiment that nobody had bothered to do. He shut the plant in a dark cupboard with no sunlight at all, and he kept watching. And the plant kept opening and closing its leaves on a daily schedule anyway, in total darkness, as if it could still feel the sun. It could no longer see. The rhythm was not coming from the sunlight. It was coming from inside the plant. That little mimosa, locked in a cupboard almost 300 years ago, was the first hint that living things carry their own internal clocks. In humans, that clock lives in a structure with an intimidating name, the suprachiasmatic nucleus, which everyone shortens to the SCN. It is a pair of tiny clusters of cells, only around 20,000 neurons total, sitting deep in the hypothalamus, right above the spot where your optic nerves cross. That last detail is not an accident, because the SCN's whole job is to keep your internal clock matched to the actual day outside, and the way it does that is by stealing information from your eyes. Here is the chain. Your eyes contain special light detecting cells, separate from the ones you see images with, and these cells care about one thing, which is how bright it is. They send a signal straight back along a dedicated pathway to the SCN, basically reporting whether it is currently daytime out there. The SCN takes that report and uses it to reset the master clock every single day, nudging it to stay locked to the real world. This is why light is the single most powerful tool you have for controlling your sleep, and why staring at a bright phone at midnight is, as far as your SCN is concerned, you screaming at it that the sun is up. When the SCN decides it is getting dark and heading toward night, it sends a message through a surprisingly roundabout chain of nerves down to a small gland in the center of the brain called the pineal gland, which the philosopher Descartes once called the seat of the soul. The pineal gland responds by pumping out a hormone called melatonin. A lot of people think of melatonin as a sleeping pill, and that is not quite right. Melatonin does not knock you out the way a sedative does. It is more like a signal, a chemical announcement spreading through your whole body that says, "It is night now. Start getting ready for sleep." It is the darkness hormone. Its levels climb in the evening, peak in the middle of the night, and fall toward morning. This is exactly why melatonin supplements confuse so many people. They buy a bottle, swallow a big dose at bedtime, expecting to be knocked out like a sleeping pill, feel barely anything, and conclude the stuff does not work. But that is using a signal as if it were a sedative. Where melatonin genuinely helps is as a timing tool, a small dose taken at the right hour to nudge the clock earlier or later, which is why it can be useful for jet lag or for the shifted clock of an extreme night owl. On top of that, the doses sold in stores are often many times larger than the tiny amount your own brain makes. So people are flooding their system with the timing signal at the wrong strength and the wrong moment, and then blaming the molecule. It is the right chemical used the wrong way, and the system is so sensitive to light that even a few minutes of bright light at the wrong time of night can slam the brakes on melatonin production. Your brain genuinely cannot tell the difference between the sun and a bright enough screen or lamp. As far as that ancient light detecting machinery is concerned, light means day, and day means shut down the melatonin, which is the mechanism behind a huge fraction of modern sleep complaints. We built a world full of artificial light and bright screens, and then we are surprised that the clock that evolved over millions of years to follow the sun gets confused. In the morning, the system runs in reverse. Light hits your eyes. The SCN shuts down the melatonin, and it triggers a rise in the hormone cortisol, which is part of what helps drag you up into wakefulness. This is also why your body temperature, your alertness, and your hormones all run on a daily wave, peaking and dipping at roughly the same times each day. There is even a built-in dip in the early afternoon, a natural low point in the wave, which is part of why so many cultures landed on the idea of an afternoon nap, and why you can feel a slump around mid-afternoon, even when you slept fine. The clock is also why people are not all the same. Some people are genuinely wired to run earlier, the morning larks who wake up sharp at dawn, and some are wired to run later, the night owls who do not come alive until the evening, and a big chunk of that is set by your biology and your genetics, not just your habits. Fighting your own chronotype, forcing a deep night owl onto a farmer's schedule is a real and exhausting thing, not laziness. Once you understand that there is a physical clock in there, being set by light and running on its own pace, a lot of modern misery suddenly makes sense. Jet lag, for instance, is not really about being tired from travel. It is the gap between the time your internal clock thinks it is and the time the new place actually is. Fly across several time zones, and your master clock is still running on home time, telling your body to sleep when the new country is having lunch, while every cell in you slowly drags itself into the new schedule over a number of days. And there is a quirk most travelers have felt without understanding. Flying east is usually harder than flying west, because flying east means you have to shift your clock earlier, and your internal clock, which naturally likes to run a touch longer than 24 hours, finds it much easier to stretch a day out than to cram one short. Shift work is jet lag that never ends, forcing yourself to be awake and working through the night when your clock is screaming that it is time to sleep, and then trying to sleep during the day when your clock is shouting that it is time to be awake, puts you in a permanent fight with your own biology. The body never fully adjusts because every day off, the person flips back toward a normal schedule, so the clock never lands anywhere. The toll of this is serious enough that night shift work involving long-term circadian disruption has been formally classified as a probable cause of cancer, and it is tied to higher rates of heart disease, weight problems, and mood disorders. Your clock did not evolve for a 24-hour economy, and it does not forgive you for pretending otherwise. There is even a milder, everyday version of this that affects almost everyone, sometimes called social jet lag. It is the gap between the schedule your body wants and the schedule your job or school forces on you. A natural night owl who has to be at work at 8 in the morning is, in effect, giving themselves a small dose of jet lag every single workday, sleeping too little on weeknights, then sleeping in to catch up on weekends, which shoves their clock later again, so that Monday morning feels like flying across two time zones. The weekend lie-in that feels so good is partly the wreckage of a clock that has been yanked back and forth all week, and one group makes the role of flight unmistakable. Many people who are completely blind, with no working light sensing in their eyes at all, cannot reset their clock to the day the way the rest of us do, because the master clock never gets the light signal it needs. So their internal clocks run free, exactly like the plant in the cupboard, drifting a little later each day, which means they cycle in and out of sync with the world around them over a period of weeks, going through stretches where their body wants to sleep all day and be awake all night, then slowly drifting back. It is one of the clearest demonstrations there is that light is not just helpful for the clock, it is the thing that holds the clock to the real world at all. But there was one giant question hanging over all of this for decades. We could see that the clock kept ticking on its own, the way the mimosa plant did in the cupboard. But how fast does the human clock actually run when you strip away the sun and the lamps and the alarm clocks and every clue about what time it is? Left completely alone in the dark, does the human body really keep a roughly 24-hour day? Or does it drift? And to answer that, one man did something genuinely insane. He went down into a cave and stayed there. In 1962, a 23-year-old French scientist named Michel Siffre climbed down into a deep cave in the Alps and stayed there, completely alone, for 2 months. He had no clock, no watch, no calendar, no radio, and absolutely no sunlight. The only people he had contact with were a team on the surface, and the contact was one way, meaning he could call up to them, but they were not allowed to tell him anything about what time or day it was. He ate when he felt hungry and slept when he felt tired, and the surface team carefully logged the real time of every single thing he did. The whole point was to find out what his body would do with time when every outside clue about time was taken away. What happened became one of the foundational results in the study of the body clock. When the team laid ciphers, sleeping and waking against a real calendar, his days did not match the world's days. His internal clock kept ticking, but it ran a little slow, settling into a cycle of roughly 24 and a half hours rather than a clean 24. A little bit of drift each day does not sound like much, but it adds up, and over 2 months, it added up enormously. When the surface team finally called down to tell him the experiment was over, Siffre did not believe them, because by his own internal count, he thought he still had weeks to go. He came out of that cave convinced it was the middle of August. The real date was the 14th of September. He had lost track of about 25 days. His body had kept time on its own, the way the mimosa plant kept opening its leaves in the dark, but with no sunlight to reset it each morning. It had slowly slid out of step with the real world, and his sense of how much time had passed was wildly, deeply wrong. This is the thing scientists came to call a free running rhythm, which just means a body clock running with no outside corrections. In normal life, you are constantly being reset by daylight, by your alarm, by meal times, by the schedules of the people around you, all of which are called Zeitgebers, a German word that means time givers. Strip all the time givers away, and the clock does not stop. It just runs free, on its own slightly off pace, the way Siffre's did. The result got serious attention, and not just from biologists. This was the height of the Cold War and the start of the space race, and suddenly the question of what the human sleep cycle does with no normal day and night was extremely relevant, both for astronauts heading into space and for crews stuck for months inside nuclear submarines. By Siffre's own account, NASA put up money to run sophisticated mathematical analysis on the data from his first cave. He had basically turned himself into the test subject for how humans handle a world with no sunrise. So, in 1972, at the age of 33, he did it again, except much bigger. This time he went down into a cave in Texas called Midnight Cave and stayed for 6 months, around 179 days, wired up to monitors, tracking his heart, his brain, and his muscle activity the whole time. And in this longer stretch, something even stranger seemed to emerge. His sleep and wake cycle did not just drift a little. At times, it appeared to balloon out toward a 48-hour day where he would stay awake for an extremely long stretch and then sleep for an extremely long stretch, living something close to a 36 hours up, 12 hours down kind of schedule without realizing it. Now, here is the twist, because this is where being careful matters. Cifre became convinced that the 48-hour cycle was a true, deep feature of the human body, and for a while, a lot of people believed him because he had seen it with his own data across multiple experiments. But later, researchers found a problem hiding in the setup. Down in those caves, the subjects controlled their own electric lighting, and the more tired they got, the more they tended to turn the lights up brighter. And every time they did that, the bright light pushed back the moment they finally fell asleep. Because, remember, light suppresses the sleep signals. Bit by bit, the subjects were unknowingly using artificial light to shove their own clocks further and further off track. When researchers in the 1990s ran the experiments again with carefully controlled lighting, that 48-hour cycle mostly vanished, and what was left was an internal clock that, just like the rest of the natural world, sits remarkably close to the length of one Earth day. The 48-hour result was largely an artifact of letting people fiddle with their own lights. It is a clean example of how a real, dramatic observation can still point to the wrong conclusion until you control the one variable you did not think about. Sifri paid a real price for all of this. He came out of the Texas cave around $100,000 in debt because the experiment had cost far more than he expected, and that debt forced him out of the field of chronobiology that he had helped create. He described lasting psychological damage from the long stretches of total isolation, and his marriage did not survive it. Decades later, near the year 2000, in his 60s, he went back into a cave one more time to study how the body clock changes with age, following the example of the astronaut John Glenn returning to space as an old man. While he was down there, he tried to celebrate the new year at the right moment, and he was off by 3 days. The lesson of the caves was always the same. The clock inside you is real, and it never stops. But without the sun to set it straight, your own sense of time quietly comes apart. Which raises the obvious next question. If there is a physical clock ticking away inside us, what is it actually made of? What is the gear and spring of a clock built out of living cells? That question took another few decades, a lab full of fruit flies, and eventually a Nobel Prize to answer. The hunt for the actual gears of the body clock started, of all places, in fruit flies, those tiny insects that gather around old bananas. Fruit flies live their whole lives on a daily rhythm, too, hatching and moving around on a schedule. And in 1971, two scientists, Seymour Benzer and his student, Ronald Konopka, went looking for flies whose clocks were broken. They found them. They found mutant flies whose daily rhythms were wrecked in different ways. Some ran short on a roughly 19-hour cycle. Some ran long on a roughly 28-hour cycle, and some had no working rhythm at all. And when they traced the cause, all three kinds of broken clock came back to damage in the same single gene. They named that gene period, A single gene could speed up the clock, slow it down, or stop it entirely. That was a huge clue, but it left the real mystery wide open, because knowing a gene controls the clock does not tell you how a gene could possibly keep time. A gene is just a stretch of instructions for building a protein. How do you get a ticking, roughly 24-hour rhythm out of that? Answering that took until the 1980s, and it took three more scientists, Jeffrey Hall and Michael Rosbash, who worked closely together, and Michael Young working separately. In 1984, they managed to isolate the period gene itself, and then they worked out the beautiful little machine it runs. Here is how the clock actually works, and it is genuinely clever. The period gene contains the instructions for making a protein, which scientists call PER. During the night, the cell reads the gene and builds up more and more protein. So the level of PER climbs higher and higher. But PER has a strange habit. As it piles up, it drifts back into the control center of the cell and switches off its own gene, telling the cell to stop making any more PER. So production halts, the existing PER slowly gets broken down and cleared away over the course of the day. The level drops, and once it is low enough, the gene switches back on and starts building PER all over again. Build up, shut yourself off, drain away, start again. That loop, all on its own, takes almost exactly 1 day to go around. The clock is a protein that turns off its own factory, and the time it takes to fill and empty is the tick. The other scientists filled in the rest of the gears. There was a second gene, fittingly named Timeless, whose protein partners up with PER and helps it do its job. And Michael Young found yet another gene, charmingly called Double Time, whose protein controls how fast PER gets built up, basically acting as the speed adjustment for the whole clock, which is exactly the kind of thing that would explain why Konopka's mutant flies ran fast or slow. For working out this little molecular clock, Hall, Rosbash, and Young were awarded the Nobel Prize in Physiology or Medicine in 2017. And the reason it mattered so much is that this exact same clockwork, the same kind of self-silencing feedback loop, is not just in fruit flies. It is in plants, in animals, and in you. And it is not only in your master clock in the brain. Nearly every cell in your body runs its own copy of this clock. Your liver has one. Your skin has one. Your heart has one. The SCN in your brain is the conductor, keeping all of them roughly in sync, using signals like light and body temperature. But the individual instruments are ticking away in tissues all over your body. That fact has a serious side. When you fly across time zones, or work night shifts, or stay up scrolling until sunrise, you are not just making your brain tired. You are pulling all of these little cellular clocks out of alignment with each other. So your liver thinks it is one time, while your brain thinks it is another. And that internal disagreement is increasingly linked to real problems with metabolism, mood, and long-term health. The clock is not a suggestion. It is wired into the chemistry of nearly every cell you have. Just how deep this goes is hard to overstate. When scientists looked at how genes switch on and off across the day, they found that something close to half of all your genes are under the control of the clock in some tissue or other, rising and falling on a daily rhythm. That means you are, in a real biochemical sense, a slightly different machine at 3 in the afternoon than you are at 3 in the morning. Your body temperature, your blood pressure, your hormone levels, your alertness, even how your body would handle a given dose of a drug, all swing on the clock. Doctors have started taking this seriously because the same medicine can work better or worse depending on the time of day it is given, and it is part of why heart attacks cluster in the morning hours. When blood pressure surges as the body ramps up for the day, the question, what time is not just something to ask a clock on the wall. It is a real question about the state of your entire body. So that is the first of the two processes, the clock, the part that decides when it should be night. But the clock alone does not explain sleepiness. After all, if you pull an all-nighter, you do not stop feeling tired just because your clock says it is technically daytime again. There is a second force at work, completely separate from the clock, and it is the one you actually feel building behind your eyes right now. It comes down to a single molecule. The second process, the pressure gauge, runs on a chemical called adenosine. Every waking minute, your brain is burning energy, and the main fuel it runs on is a molecule called ATP. When your cells use up that fuel, one of the leftover scraps they produce is adenosine. So the longer you are awake, the more your brain works, and the more adenosine builds up in it, slowly, all day long, like sand filling the bottom of an hourglass. And adenosine is not just waste. As it accumulates, it starts plugging into specific docking points on your brain cells. And when it does, it quiets down the neurons that keep you awake and alert. The more adenosine that piles up, the harder it presses on those wake systems and the sleepier you feel. That heavy, foggy, eyes pulling shut feeling you get late at night is, in large part, the physical sensation of adenosine flooding your brain. It is your sleep pressure, your sleep debt, made out of an actual molecule you can measure. Then you sleep, and your brain clears the adenosine back out, draining the hourglass, so that you wake up in the morning with the pressure reset to near zero and the whole thing starts filling again. This is the second half of the two-process model. The clock says when it should be night, and the adenosine says how badly you need sleep. And the two normally line up so that your sleep pressure is highest right around the time your clock is telling you it is night. When they do not line up, like when you have been awake for a full day and then fly into a new time zone, you get that miserable state of being completely exhausted and completely unable to sleep at the same time. These same two systems explain a couple of everyday mysteries about waking up. Have you ever woken up on your own a minute or two before your alarm goes off, almost as if your body knew that is the clock at work? When you keep a regular schedule, your clock learns your wake time and starts preparing for it in advance, releasing a rising pulse of the hormone cortisol in the last hour or so of sleep to ramp your body up toward waking, so that a well-scheduled body can rouse itself right on cue, no alarm required. Your body is not guessing, it is anticipating. And the flip side is that groggy, thick-headed barely human feeling you sometimes get right after waking, where you cannot think straight for a while. That has a name, sleep inertia, and it usually means your alarm hauled you up out of deep, slow wave sleep, the heaviest stage before your brain was ready to surface. Yanked out of the depths, the brain takes time to fully come back online, which is why those first groggy minutes can feel almost drunk. Wake up naturally at the end of a cycle from lighter sleep and you come up clean. This is also why a short nap can leave you sharp, while a longer one leaves you wrecked, because the long nap drops you into deep sleep and then the alarm rips you out of it. And it is part of why slapping the snooze button and tumbling back into a new sleep cycle, only to be wrenched out of it again 9 minutes later, can leave you groggier than if you had just gotten up the first time. There is one more trick the clock plays that everyone has felt without understanding. The clock does not only make you sleepy at night, it also actively pushes your alertness up during the day to counteract the rising adenosine, so that you stay functional even as the pressure builds. And here is the strange part. That alerting push from the clock actually peaks in the couple of hours right before your normal bedtime in a window researchers call the wake maintenance zone. So you can be dead tired at 9 in the evening, dozing on the couch, and then somehow feel wide awake again at 11. That is not random. It is the clock throwing one last burst of alertness to hold you up until the proper time to sleep, briefly overpowering the adenosine. It is also why a night owl ordered to bed at 9 will often just lie there staring at the ceiling, because they have been sent to bed in the middle of their strongest alerting signal of the day. Only when that signal finally falls away does the gate swing open and the built-up pressure get to pull you under. Now, knowing all this, you can finally understand exactly what the most popular drug on the planet is doing to you. Caffeine is the most widely used psychoactive substance in the world, and the way it works is almost sneaky. Caffeine does not give you energy. It does not reduce your adenosine. What it actually does is fit into the exact same docking points that adenosine uses and block them, like jamming a key into a lock so the real key cannot get in. The adenosine is still there. Your sleep pressure is still building, but your brain can no longer read the signal because caffeine is sitting on the receptors, so you simply do not feel how tired you actually are. That sounds great, and for a few hours it is, but there is a catch built into the chemistry. Caffeine has a half-life of roughly 5 to 6 hours, which means that something like half of the caffeine from a cup of coffee is still floating around in your system 5 or 6 hours later. So if you have a strong coffee at, say, 4 in the afternoon, a real chunk of that caffeine is still actively blocking your adenosine receptors at 10 at night, quietly sabotaging your ability to fall asleep even if you feel fine. And there is a second sting. While the caffeine was blocking your receptors, the adenosine never stopped piling up behind it. So, when the caffeine finally wears off and clears out, all of that backed up adenosine floods onto the now open receptors at once, which is the afternoon crash, the sudden wall of exhaustion that hits a few hours after the coffee that was keeping you going. You did not get free energy. You took out a loan, and the adenosine came to collect with interest. It also explains why a nap can be so powerful and why timing it matters. A short nap gives your brain a chance to clear out some of that adenosine, which is why even 10 or 20 minutes can leave you feeling genuinely sharper since you have actually drained a bit of the pressure rather than just masking it. But nap too long and you sink down into deep, slow wave sleep, and getting yanked out of that leaves you groggy, which is why a too long nap can feel worse than no nap at all. The whole strange ritual of human alertness, the morning coffee, the afternoon slump, the power nap, the wired sleepless night after too much late caffeine, all of it is just you pushing and pulling on this one molecule and the dogs it plugs into. Two other everyday substances are worth pausing on here because people get them exactly backwards. The first is alcohol. A nightcap feels like it helps you sleep because alcohol is a sedative and it does make you drift off faster. But that is a trap because alcohol badly damages the quality of the sleep that follows. It suppresses your REM sleep, the dreaming, memory, and emotion processing kind. And as your body breaks the alcohol down over the second half of the night, it fragments your sleep, jolting you up toward waking again and again, which is why a few drinks so often leads to that wired, unrefreshing 3 in the morning kind of night. You fall asleep faster and you rest far worse, which is close to the worst possible trade. The second is the fact that caffeine does not hit everyone the same way, and a lot of that is genetic. People carry different versions of the genes that control how fast the liver breaks caffeine down. So some people are fast metabolizers who can drink an espresso after dinner and sleep like a baby, while others are slow metabolizers in whom a single morning coffee is still actively jamming their adenosine receptors at bedtime. On top of that, with regular use, your brain adapts by building more adenosine ducts, which is why long-term coffee drinkers need more to get the same lift, and why suddenly quitting brings on that pounding withdrawal headache, as all that extra docking machinery suddenly gets flooded by adenosine with nothing blocking it. So when someone swears caffeine does not affect their sleep, they might be right about themselves and completely wrong about you. Now, remember all the way back to Von Economo, the doctor who looked at damaged brains and predicted there had to be a dedicated on switch and off switch for sleep built into the brain. He was right, and we now know roughly how it works, and it is wonderfully clever. There is a small cluster of cells deep in the brain that acts as the off switch, and when it fires up, it actively shuts down the various regions that keep you awake and alert. And those wake promoting regions, in turn, shut down the off switch. The two sides inhibit each other, like the two ends of a seesaw, where pushing one down automatically lifts the other up. Engineers have a name for a circuit built like that, a flip-flop switch, and it is designed to do one specific thing, which is to snap cleanly into one state or the other and refuse to get stuck halfway. That is exactly what you want for sleep, because a brain that drifted around half awake and half asleep would be useless and dangerous, so the switch is built to commit. When the wake side wins, you are firmly awake. When the sleep side wins, you are firmly asleep. The two clocks we just covered, the circadian timing and the adenosine pressure, are basically what tip the seesaw one way or the other at the right time of day. But a seesaw can be unstable, prone to flipping back and forth, so the brain adds one more piece, a stabilizing signal that holds the switch firmly in place once it commits, preventing it from flipping at random throughout the day. And here is a thread to hold onto because it is going to pay off later in a big way. There is a specific brain chemical whose entire job is to be that stabilizer, to keep the switch locked in the waking position when you are supposed to be awake. And in a certain devastating disorder, the cells that make that chemical get destroyed, the stabilizer disappears, and the switch starts flipping uncontrollably, dumping people straight from waking into sleep and even into the paralysis of dreaming at the worst possible moments. We will get to exactly what that chemical is and what happens when it is gone. So now we have the full picture of when and how hard sleep hits you. The clock in your brain, built out of self-silencing genes and set each day by light, decides the timing. The adenosine, built out of the leftover fuel of a working brain, decides the pressure. Together they pull you down into that structured nightly program of stages and cycles. Which brings us, finally, to the question that haunted the entire field for the better part of a century. We know when, we know how, but why? Why does the brain bother doing any of this? What is so important that evolution decided it was worth leaving you blind, deaf, paralyzed, and helpless for a third of your entire life? For a long time, the honest answer to why we sleep was that nobody really knew, and that is a genuinely strange thing to admit about something so universal. Every animal that has been carefully studied sleeps or does something very much like it, from elephants down to fruit flies. Evolution is ruthless about wasted time, and being asleep is about the most vulnerable state imaginable, lying there unconscious and unable to react while predators roam around. If sleep were not doing something absolutely essential, evolution should have gotten rid of it long ago. The fact that it survived in basically every creature with a nervous system tells you it must be paying for itself somehow. The question was just how. The oldest idea was energy conservation. The thinking was that sleep is a way to power down and save fuel during the hours when you cannot do much useful anyway. There is something to this because your metabolism does drop while you sleep. But when scientists actually measured the savings, they were underwhelming. The energy you save over a full night of sleep compared to just lying still and resting is modest, roughly the amount in a small snack. That is nowhere near enough to justify shutting your entire brain and body down and leaving yourself defenseless for 8 hours. If saving a snack's worth of calories were the only point, sleep would be a terrible deal. So energy conservation might be part of the answer, but it cannot be the whole thing. Another old idea flips the danger argument on its head. Instead of asking why evolution would risk leaving you defenseless, it suggests that sleep is itself a safety strategy, a way of forcing an animal to stay still, silent, and hidden during the hours when it is most vulnerable or least able to function. A small animal that cannot see well in the dark is arguably safer, tucked away, motionless in a burrow, than blundering around in the night where predators can hear it. So shutting down and lying low might keep it out of trouble. And there is real support for this in the timing, because different animals sleep at the times of day that are most dangerous or least useful for them, fitting their sleep into the safest window they have. But this one also cannot be the whole story, because evolution could have achieved stay still and stay hidden with simple, quiet rest, without the steep price of going fully unconscious, paralyzed, and blind to an approaching predator. Genuinely switching off is far riskier than just holding still. So this theory explains when animals sleep much better than it explains why sleep has to involve losing consciousness at all. The next idea was restoration, the common sense notion that sleep is for repair, that the body uses the downtime to fix and rebuild itself. And this one holds up much better. As we saw, deep slow wave sleep is when most of your growth hormone is released, when tissue repair ramps up, and when a lot of the maintenance work on your body gets done. Your immune system leans heavily on sleep too, which is why you get knocked flat and sleep for hours when you are sick, and why people who are chronically short on sleep get sick more easily and heal more slowly. Restoration is clearly a big piece of the puzzle for the body, and the body effects go far beyond simple repair into places people rarely connect to sleep at all. Take hunger. Your appetite is steered by a pair of hormones that work against each other. One that tells your brain you are full, and one that tells your brain you are hungry. When you cut your sleep short, the fullness signal drops and the hunger signal climbs. So you wake up hungrier than you should be. And worse, your cravings shift toward sugary, fatty, high calorie food. This is a big part of why poor sleep is so tightly linked to weight gain. It is not a lack of willpower. It is that a tired brain is being chemically told it is starving even when it is not, and then handed a craving for exactly the worst foods. It reaches into your blood sugar too. Studies have taken healthy young people, restricted their sleep for just a handful of nights, and watched their bodies start handling sugar noticeably worse, drifting toward the kind of insulin resistance you see in the early stages of diabetes, all from a week of short nights. The effect reverses when they sleep properly again, but it shows how quickly skimping on sleep starts pushing the body's chemistry in a dangerous direction. And the immune connection is more than just getting sick more often. In one striking line of research, people were deliberately exposed to a cold virus, and the ones who had been sleeping poorly were several times more likely to actually come down with the cold than the ones who had slept well. In another, people were given a vaccine and then either allowed to sleep normally or kept short on sleep, and the well rested group produced a substantially stronger antibody response. In plain terms, a good night of sleep makes a vaccine work better, and a bad one blunts it. Your immune system does a real chunk of its work while you are unconscious, and shorting it on sleep leaves you more exposed. Even raw physical performance lives and dies on sleep. Reaction time, accuracy, coordination, and the risk of getting injured all get measurably worse when athletes are short on sleep, and studies that simply have athletes sleep more have found their speed, accuracy, and performance improve, sometimes dramatically. The body you take into the gym or onto the field the day after a bad night is, in a very real sense, a slower, clumsier, more fragile version of you. But here is what kept nagging at scientists. The body could, in principle, do most of that repair while resting quietly, without ever going unconscious and paralyzed. Resting your muscles does not require switching off your awareness of the world. So, restoration explains why sleep is good for the body, but it does not explain the strangest part, which is why the brain insists on going offline. Why does the brain specifically need you to lose consciousness? Whatever the deepest reason for sleep is, it has to be something the brain can only do when it disconnects from the outside world. And over the last few decades, two answers to that have emerged that are genuinely jaw dropping, and they are not in competition because the brain appears to be doing both at once. The first answer is about information. Your brain spends the night sorting, filing, and locking in everything you learned during the day in a process called memory consolidation, and it cannot do this properly while you are awake and busy taking in new information. The second answer is even more startling and was only nailed down in the last 15 years or so. Your brain physically washes itself while you sleep, opening up channels and flushing out toxic waste that builds up during the day, including the exact kind of gunk linked to Alzheimer's disease. The brain has a plumbing system and it runs mostly at night. Let us take them one at a time, starting with what your brain is secretly doing with your memories while you lie there unconscious. When you learn something during the day, a new fact, a new route home, a new skill, that memory does not just get carved permanently into your brain on the spot. It gets parked temporarily in a seahorse shaped structure deep in your brain called the hippocampus. The hippocampus is fast at grabbing new memories, but it is small and it works more like a temporary holding bay than a permanent archive. The permanent storage is spread out across the vast outer surface of your brain, the cortex. So at some point, those memories have to be moved from the temporary bay into long-term storage, and the brain does the bulk of that moving at night while you sleep. This is memory consolidation. The way it does it is genuinely wild to picture. During deep sleep, the hippocampus replays the day's memories, firing off the same patterns of neurons that fired when the event first happened, except sped up, compressed, sometimes played back many times faster than the original. Things that took minutes to experience get replayed in fractions of a second. Researchers have watched this directly in the brains of sleeping animals, seeing the neural pattern of a maze the animal ran that day get replayed in fast forward overnight. Again and again, the brain is rehearsing. It is running the tape of your day over and over in the dark, and each replay helps shift the memory from the temporary hippocampus into the permanent cortex. And this replay is not random. It is tied to those electrical signatures we met earlier in the sleep stages. Remember the sleep spindles, those quick bursts during N2, and the big, slow waves of deep sleep. It turns out the brain carefully coordinates these. The hippocampus fires off its compressed replay during sharp little bursts of activity. The cortex produces its slow waves, and the sleep spindles fire in tight time with both, all three, locking together in a precise rhythm. That coordination is what lets the memory get handed off cleanly from one part of the brain to another. The better and more tightly these rhythms line up during your sleep, the better you actually remember the material the next day. Your spindles are, in a real sense, the brain stitching the day into permanent memory. The different stages handle different kinds of memory too. The deep, slow wave sleep, heavy in the first half of the night, is especially important for facts and events, the kind of memory you can put into words, like a list of vocabulary words or where you parked. REM sleep, heavy in the second half of the night, seems to be more involved in skills, in emotional memories, and in weaving new information together with things you already knew, finding connections and patterns. This is part of where the old advice that you should sleep on a hard problem comes from, because there is real evidence that sleep helps the brain reorganize information and sometimes crack problems that you could not solve while awake. There is one experiment here that is too good not to tell, because it shows the dreaming brain caught in the act of consolidation. Researchers had people play the falling block puzzle game Tetris for hours and then studied them as they fell asleep. As the players drifted off, a large share of them reported seeing the same thing in that twilight state at the edge of sleep, falling, rotating Tetris blocks, the game bleeding directly into the onset of their dreams. That alone is a neat result. But the researchers had also included a group of people with severe amnesia, people whose memory damage was so profound that they could not consciously remember having played the game at all. And those amnesiac patients still reported the falling blocks as they drifted off. They had no memory of playing, yet their sleeping brains were clearly still chewing on the experience, replaying the shapes the game had burned in. The consolidation machinery was running underneath, below conscious memory entirely. Now, here is a part of the memory story that surprises almost everyone, which is that sleep does not only help you lock in what you learned, it also prepares your brain to learn in the first place. Remember that the hippocampus is the temporary inbox where new memories land before they get filed. That inbox has limited space, and over a day of learning, it fills up. A night of sleep is partly what empties it by shifting the day's memories into long-term storage and clearing the inbox so it is ready to take in new things the next morning. Researchers have shown this directly. People kept awake are noticeably worse at forming brand new memories the following day, as if their inbox is jammed full with nowhere to put anything new. So sleep matters on both ends of learning. The night before to have a clear inbox ready to absorb, and the night after to file away what you took in, which means pulling an all-nighter before an exam is doubly foolish. You learn worse going in because your inbox was never cleared, and then you never get the night that would have filed it. And there is an even stranger gift sleep gives, especially for skills. Take something physical and learnable, a tricky run on a piano, a sequence on a keyboard, a move in a sport. You can practice it hard, hit a plateau where you stop improving and walk away. And then, with no further practice at all, just a night of sleep, you can wake up the next day measurably better at it than you were when you stopped. Studies have measured this carefully, and the improvement is specifically tied to the sleep, not just to the passage of time, because people who stayed awake for the same number of hours do not get the same boost. Your brain appears to rehearse and refine the skill overnight, smoothing it out while you are unconscious, so that you genuinely level up in your sleep. The old advice to sleep on, it turns out to be true, not just for decisions, but quite literally for your hands. Now, for a long time, the assumption was that sleep helps memory by strengthening the connections in your brain, making the important links bigger and stronger. But two scientists, Giulio Tononi and Chiara Cirelli, put forward a different and slightly mind-bending idea, the synaptic homeostasis hypothesis. Their argument runs like this. All day long, as you learn and experience things, the connections between your brain cells get stronger and more numerous, because that is what learning is. But this cannot go on forever. If your connections only ever got stronger, your brain would eventually saturate, run out of room, burn too much energy, and lose the ability to tell a meaningful signal from background noise, because everything would be turned up to maximum. So their idea is that the main job of sleep, especially deep sleep, is to turn the volume back down across the board. Overnight, the brain weakens and prunes its connections, scaling them all back down toward a sustainable baseline. But it does this unevenly. So the strongest and most important connections survive the cut, while the weak, trivial ones get trimmed away. The result is a brain that wakes up clearer, more efficient, with the important stuff still standing out from the noise, and with room to learn again. In their words, sleep is the price the brain pays for being able to learn at all. You cannot keep absorbing new things during the day without a nightly reset that clears out the junk and protects the signal. By that view, a sleepless brain is not just tired, it is a brain that has run out of room and can no longer tell what matters. And this is not just a nice theory, because there is now physical evidence you can almost hold in your hand. Researchers used extremely powerful microscopes to actually measure the size of the connection points between brain cells in mice, comparing brains after sleep with brains after waking. And the connections were measurably smaller after sleep, shrunk down by something like a fifth on average, exactly as the theory predicted, with the change sparing the largest, strongest connections. You can literally see the brain physically dialing itself back down overnight, trimming the previous day's growth so it can grow again the next day. Whether sleep is mostly strengthening the good memories or mostly pruning back the noise so the good ones stand out, the field is still working out the balance, but both point at the same underlying truth, that the sleeping brain is actively reshaping itself, not resting. Whichever way the details shake out, and the field is still arguing about exactly how much is strengthening versus pruning, the core point is solid and well proven. A huge part of what your brain is doing while you are unconscious is managing your memory, deciding what to keep, filing it into permanent storage, weaving it into what you already know, and clearing space for tomorrow. Pull an all-nighter before an exam, and you do not just feel tired, you have literally skipped the step where the studying gets locked in. The brain was supposed to do the filing at night, and you never gave it the night. And that is only the first of the two great functions. Because while your brain is busy sorting your memories, it is also, at the very same time, running a cleaning crew that scientists did not even know existed until about a decade ago. All day long, while your brain burns through fuel and fires off billions of signals, it produces waste, the leftover trash of all that activity. Every other organ in your body has a way to drain that kind of waste away. Your body has the lymphatic system, a network of vessels that carries off cellular garbage and dumps it where it can be cleaned up. But the brain, strangely, has no lymphatic vessels of its own, and for a long time this was a genuine puzzle. The most metabolically demanding organ you have, producing the most waste, somehow had no obvious garbage collection. So where does the trash go? Around 2012, a research team led by a scientist named Maiken Nedergaard found the answer, and it is remarkable. The brain does have a waste clearance system. It had just been hiding in plain sight, and they named it the glymphatic system. Here is roughly how it works. Your brain is bathed in a clear liquid called cerebrospinal fluid. That fluid gets pushed in along tiny tunnels that run alongside your blood vessels, deep into the brain tissue, where it mixes with the fluid around your brain cells, picks up all the accumulated waste, and then flushes back out along other channels, carrying the garbage away to be disposed of. It is, in effect, a plumbing system, a way of power washing the brain from the inside, using its own fluid. Part of why this took until the 21st century to find is almost embarrassing in hindsight. For generations, brains were mostly studied dead on a slab, and in a dead brain, this whole fluid system collapses and drains away, leaving no trace, so it simply was not there to be seen. It was only when newer technology let scientists peer into the brains of living, sleeping animals, watching the fluid actually move in real time using glowing tracers and powerful microscopes, that the hidden plumbing revealed itself. The cleaning system had been operating inside every human skull for as long as there have been humans, and we missed it entirely because we kept looking at brains that had already shut it off. But the part that connects all of this back to sleep came the next year, in 2013, in a study published in the journal Science. And it is the kind of finding that reframes everything. The team discovered that this cleaning system barely runs while you are awake. It switches into high gear when you sleep. When they looked at the brains of sleeping mice, they found that the spaces between the brain cells actually opened up, expanding by around 60%, the cells themselves shrinking to make room, which let the cleaning fluid rush through far more freely. The flow of fluid into the brain was something like 10 times greater during sleep than during waking. The brain physically changes shape at night to let the cleaning crew in. And here's the detail that turns this from interesting into genuinely important. One of the specific pieces of waste this system flushes out is a sticky protein called beta amyloid. That name might ring a bell because beta amyloid is the exact substance that builds up into the clumps and plaques found in the brains of people with Alzheimer's disease. In the sleeping brain, beta amyloid gets cleared out roughly twice as fast as in the waking brain. So, sleep is quite literally the time when your brain washes away one of the main substances linked to dementia. You can probably see where this is going, and the implication is sobering. If the brain only does its deep cleaning properly during sleep, then chronically robbing yourself of sleep means chronically leaving more of that toxic gunk sitting in your brain, night after night, year after year. Studies have found that even a single night of poor sleep can measurably raise the level of beta amyloid in a human brain. Over a lifetime, the growing evidence is that bad sleep and the buildup that drives Alzheimer's feed into each other in a vicious circle, where poor sleep lets more amyloid accumulate, and the accumulating amyloid in turn damages the very brain regions that produce deep sleep, making the sleep even worse. It reframes that groggy feeling after a bad night entirely. It is not just that you are tired, it is that the cleaning never properly happened, and your brain is, in a small way, sitting in its own unwashed waste. When people say sleep is restorative, this is one of the most concrete and physical things they could possibly mean. The brain spends your nights flushing itself out, and it cannot do the job while it is busy running your waking life. So now we have a real answer to the why. Sleep is not one thing for one reason. It is at least the body repairing itself, the brain consolidating and pruning your memories, and the brain physically washing out its own waste. And all of these are jobs that mostly cannot be done while you are awake and engaging with the world, which finally explains why evolution was willing to leave you unconscious and defenseless for a third of your life. The cost of being switched off is huge, but the jobs that get done in that window are non-negotiable. Skip them, and you do not just feel bad, things start to break. And the rest of this story is about what breaking looks like, starting with the strangest part of sleep of all, the part that happens behind your eyes every single night, your dreams. Everyone dreams, even people who swear they never do, because the truth is, they simply do not remember them. Most dreaming happens during REM, that paradoxical state where the brain is roaring and the body is paralyzed, although it is now clear that some dreaming happens in other stages too. The vivid, story-driven, often deeply weird dreams, the ones with plots and faces and impossible logic, those cluster in REM, which is why they pile up in the second half of the night when REM is at its longest. By the time you wake up naturally, you have usually just come out of a long REM period, which is exactly why You so often wake up mid-dream. For most of human history, dreams were treated as messages, either from the gods or, in the early 20th century, from a hidden part of the mind. Sigmund Freud built a whole empire on the idea that dreams were disguised wishes, coded messages from the unconscious that a trained analyst could decode. Then, in 1977, a Harvard psychiatrist named Alan Hobson, working with a colleague, Robert McCarley, proposed something that infuriated the Freudians, an idea called the activation synthesis hypothesis. Their argument was that dreams might start as something close to noise. During REM, the lower, more primitive part of the brain, the brainstem, fires off bursts of essentially random signals up into the higher brain. The higher brain, which spends your whole waking life trying to make sense of incoming information, does the only thing it knows how to do. It tries to weave those random signals into a story. The bizarre, jumping, dreamlike quality of dreams, where you are somewhere, then suddenly somewhere else, where people change identity and the rules of physics bend, would be the result of your storytelling brain desperately trying to stitch a coherent narrative out of random sparks. The dream is not a hidden message. It is your brain improvising a plot from noise. The chemistry of the dreaming brain backs a lot of this up, and it explains one of the most annoying facts about dreams, which is how fast they evaporate. During REM, the brain turns down the chemicals it normally uses to lay down new memories and stay logical. In particular, a pair of signaling chemicals that keep your waking mind organized and able to record what is happening, while it cranks way up a different chemical that is tied to vivid internal imagery. In other words, while you are dreaming, the very systems that would normally save the dream to memory are switched off. The dream is happening in a brain chemically configured not to remember it, which is why a dream that felt completely real and gripping can vanish within seconds of opening your eyes, leaving you with only the fading sense that something happened. But activation synthesis is not the whole story, because dreams are not as random as pure noise would predict. They have patterns. And so, other scientists proposed that dreams actually do something useful. One influential idea, the threat simulation theory, points out that dreams are heavily skewed toward bad things. Studies of dream content find that fear, being chased, and misfortune show up far more often than happy, pleasant scenes, and that the bad stuff usually happens to the dreamer. The proposal is that dreaming evolved partly as a kind of overnight safety drill, a way for the ancient brain to rehearse dangerous situations, being chased, being attacked, falling, in a safe, simulated environment, so that it would be better prepared to handle them in real life. By that view, your nightmares are a feature, not a bug, the descendants of an ancient survival rehearsal. But the same machinery can get stuck, and when it does, it becomes a genuine disorder. Some people suffer chronic, recurring nightmares that wreck their sleep night after night. And this is especially common in people who have lived through trauma, where the overnight processing seems to jam, replaying the same terror on a loop instead of slowly diffusing it the way dreaming is supposed to. There is, encouragingly, a treatment for this that sounds almost too simple to work. It is called image rehearsal therapy, and the idea is that while awake during the day, the person takes their recurring nightmare and deliberately rewrites it, inventing a new, less threatening ending, and then mentally rehearses that new version over and over. Remarkably, doing this while awake tends to reduce the nightmares at night, as if the person is reprogramming the script their sleeping brain keeps reaching for. It is a small but striking demonstration that we are not entirely helpless passengers in our own dreams. There is also strong evidence that dreaming, especially in REM, helps process emotions and difficult memories. The idea is that REM sleep lets you replay emotionally charged experiences in a setting where the stress chemicals are turned down, so that over time the memory itself softens and you keep the lesson without keeping the raw sting. It is part of why a problem that feels unbearable at night so often feels more manageable in the morning, and why sleep loss is so tightly linked to anxiety and emotional fragility. When you do not get your REM, you do not get that overnight emotional processing, and everything hits harder and stays sharper than it should. A few facts about dreaming put the whole thing in perspective. You dream every single night, whether you recall it or not. And over an average lifetime, you will spend something like 6 years of your life dreaming, 6 years of vivid, fully experienced internal movies that you will almost entirely forget. The forgetting is staggering in scale because we lose the large majority of a dream within minutes of waking, which is why you can wake up certain you were just deep in some elaborate story and feel it dissolve before you can even describe it. Time inside dreams roughly tracks real time, by the way, despite the common belief that a long dream happens in an instant. And contrary to old assumptions, most people dream in full color, not black and white. Dreams also share strange common themes across totally different people and cultures, which is part of what made researchers suspect they are doing something patterned rather than random. Being chased, falling, losing teeth, showing up unprepared for an exam, being caught out in public with no clothes on. These recur again and again in people who have never met and share nothing but being human, which hints at deep shared wiring underneath. And recurring dreams, the same scenario returning night after night, year after year, tend to cluster around unresolved stress, which fits neatly with the idea that dreaming is partly the mind working over things it has not finished digesting. Even people who are blind dream, though those blind from birth tend to dream in the senses they actually use, in sound and touch and smell rather than images, which tells you a dream is built from whatever raw material a particular brain has to work with. Now here is one of the strangest corners of all of this. Most of the time, while you dream, you have no idea you are dreaming. You simply accept the absurd events as real. But some people, in some dreams, suddenly realize they are dreaming while it is still happening and can even start to control it. This is called lucid dreaming, and for a long time scientists were not sure it was even a genuine thing rather than just people remembering it wrong. It was proven real by a beautifully clever experiment. Remember that during REM, your body is paralyzed, except for your eyes, which keep moving. So, a researcher named Stephen LaBerge had lucid dreamers agree before sleep to make a specific pattern of deliberate eye movements, like looking sharply left, right, the moment they realized they were dreaming. And sure enough, the sleeping subjects, deep in REM, produced exactly those agreed eye movements on cue, sending a deliberate signal out from inside the dream to the researchers watching the readout. It was, in a real sense, the first message ever sent from a dreaming mind to the waking world. And remember Juvet's cats from earlier, the ones that acted out their dreams when the paralysis switch was disabled. In some people, that exact thing happens in real life, a condition called REM sleep behavior disorder, where the paralysis fails to kick in and the person physically acts out their dreams, kicking, punching, shouting, sometimes leaping out of bed, all while fully asleep and dreaming. It mostly affects older men, and there is a quietly alarming twist to it. For many people, REM sleep behavior disorder turns out to be an early warning sign, sometimes appearing years or even decades before, of Parkinson's disease and related conditions. The failure of the dream paralysis switch can be the first visible crack of a neurodegenerative disease still hiding underneath. The opposite failure is just as unsettling. Sometimes the paralysis of REM lingers for a few seconds after you have woken up, so your mind comes online while your body is still switched off, and you find yourself awake, aware, and completely unable to move. This is sleep paralysis, and it is terrifying but harmless and surprisingly common. Because the dreaming brain is still partly running as you surface, people in sleep paralysis often also hallucinate a presence in the room, a figure, a weight on the chest, a sense of dread, which is almost certainly the source of countless old stories across cultures about night demons, hags sitting on sleepers, and shadowy intruders. People were not lying. Their REM dream machinery was simply bleeding into the first few seconds of waking while their body refused to move. So dreams sit right at the heart of what makes sleep so strange, a nightly theater your brain stages for itself, possibly out of noise, possibly to rehearse danger, possibly to file away your feelings, and almost designed to be forgotten. But for all their weirdness, dreams are sleepworking as intended. The real horror starts when sleep itself stops working. And to understand how badly that can go, we need to talk about what happens to a person when sleep starts to break down. There are dozens upon dozens of recognized sleep disorders, and the discovery of REM is basically what created the entire field of sleep medicine that studies them. The most familiar one is insomnia, which is not just one thing, but a whole family of problems. Trouble falling asleep, trouble staying asleep, or waking far too early, often driven by stress, anxiety, pain, or a body clock that has slipped out of sync with the schedule the person is trying to keep. Insomnia is brutal partly because it feeds on itself, since the more you lie there worrying about not sleeping, the more wired and alert you become, which is the opposite of what you need. But as common and miserable as insomnia is, it is not the most physically dangerous of the common disorders. That title goes to one that millions of people have without even knowing it. Before we get to that one, it is worth naming a whole category of problems that get mistaken for insomnia, but are really something else. Disorders not of sleep itself, but of timing, where the sleep machinery works perfectly and is simply set to the wrong hour. The most common is the extreme night owl pattern, where a person's clock is shifted so late that they genuinely cannot fall asleep until the small hours of the morning, no matter how early they get into bed, and then cannot drag themselves up for work or school. It looks like insomnia plus laziness, and it gets treated as a character flaw. But it is a clock problem, very common in teenagers and young adults. And forcing an early bedtime simply means lying awake for hours. There is a mirror image too, more common in older people, where the clock runs so early that they fall asleep in the early evening and wake fully alert at 3 or 4 in the morning. The fix for these is not sleeping pills. It is carefully moving the clock itself, using precisely timed light exposure and sometimes a small dose of melatonin at the right hour to drag the rhythm back into line with the world. Treat the clock, not the sleep. It is called obstructive sleep apnea, and the basic problem is simple and frightening. While the person sleeps, the soft tissue at the back of their throat relaxes and collapses, blocking the airway so they stop breathing. The oxygen in their blood starts to drop, and after some seconds, or sometimes well over a minute, the brain detects the emergency and jolts the body into a brief, partial awakening, just long enough to gasp the airway open again. Then they sink back down, and it happens again. In severe cases, this can repeat dozens, even hundreds of times a night. The person usually has no memory of any of it. All they know is that they snore loudly and that no matter how many hours they spend in bed, they wake up exhausted because they were never allowed to stay in deep sleep, getting yanked toward waking every time their breathing failed. The scale of this is genuinely staggering. By recent estimates, something approaching 1 billion people worldwide have some degree of obstructive sleep apnea, and the large majority of them are undiagnosed, walking around chronically exhausted with no idea why. And it is not harmless. All those repeated drops in oxygen and jolts of stress night after night hammer the cardiovascular system, and untreated sleep apnea is strongly linked to high blood pressure, heart disease, stroke, and a long list of other problems, on top of the daytime sleepiness that causes car crashes and accidents. The treatment for it has a surprisingly recent origin. Before 1981, one of the only real options for severe cases was drastic, a surgical hole cut into the windpipe to bypass the collapsing throat entirely. Then, an Australian physician named Colin Sullivan came up with a much simpler idea. What if, instead of cutting anything, you just used a machine to gently blow a steady stream of pressurized air through a mask into the airway, enough to hold the collapsing tissue open like air in a balloon? That device became the Continuous Positive Airway Pressure Machine, the CPAP, and it is now the standard treatment used by millions of people every night. An air pump that quietly keeps their throat open so they can finally sleep through the night and breathe the whole time. The mask is not glamorous, but for a person with serious apnea, it can be the difference between a wrecked life and a normal one. If sleep apnea is the disorder of the body failing to breathe during sleep, narcolepsy is the disorder of the boundary between sleeping and waking falling apart altogether. People with narcolepsy are overwhelmingly, cripplingly sleepy during the day and can drop into sleep suddenly and without warning. But the truly bizarre symptom, the one that defines the most severe form, is called cataplexy. Cataplexy is a sudden, total loss of muscle strength triggered by strong emotion, often something as ordinary as laughing hard or being surprised. The person stays fully conscious, but their body goes limp, their knees buckle, their head drops, and they may collapse to the floor, all because they laughed at a joke. If that sounds familiar, it should, because it is exactly the muscle paralysis of REM sleep, the same switch Jouvet found in his cats, except it is firing at completely the wrong time, while the person is wide awake. That was the big clue. Narcolepsy looked like a disease where the walls between the sleep states had collapsed, where REM and its paralysis could come crashing into waking life uninvited. But for over a century, nobody knew what actually caused it. The answer came in 1999, and it came partly from dogs. A researcher at Stanford named Emmanuel Mignot had spent roughly a decade maintaining a special colony of dogs that had an inherited form of narcolepsy, dogs that would go limp and collapse with cataplexy when they got excited. For instance, at feeding time, Mignot and his team painstakingly hunted through the dog's genes, narrowing the search down and down until they pinned the cause to a single gene. That gene held the instructions for a receptor, a docking point for a brain chemical called orexin, also known as hypocretin. In the narcoleptic dogs, that docking point was broken. At almost exactly the same time, and without knowing about the dog work, another team led by Masashi Yanagisawa was studying mice that had been genetically engineered to lack orexin entirely. And those mice, they discovered, developed something that looked just like narcolepsy, collapsing and falling into sleep. Two teams, working on two different animals, had landed on the same molecule from opposite directions. Orexin was the missing piece. And what orexin does makes the whole disease snap into focus, because orexin is the stabilizer chemical we left hanging earlier, the one whose job is to hold the sleep switch firmly in place. Orexin is essentially the brain's stay awake signal. It is produced by a small group of neurons in the hypothalamus, and its job is to lock you firmly into the waking state and keep the sleep systems, including REM, switched off until the proper time. When researchers then examined the brains of humans with narcolepsy, they found the cause: those people had lost the orexin producing neurons, sometimes the vast majority of them. With the stabilizer gone, nothing was holding the flip-flop switch steady, so it began flipping uncontrollably, letting sleep, and especially REM with its paralysis, come flooding through at any moment, which is daytime sleep attacks and cataplexy and the dreamlike hallucinations and sleep paralysis that often come with the condition. It was called the most important advance in sleep science since the discovery of REM itself. But that left one more question. What was destroying the orexin neurons in the first place? The leading suspicion was that narcolepsy was an autoimmune disease that in genetically susceptible people, the immune system mistakenly identifies the orexin neurons as a threat and kills them off. For years, that was a strong theory without a smoking gun. And then, tragically, the world got one. During the swine flu pandemic of 2009 and 2010, a flu vaccine called Pandemrix, made by the drug company GlaxoSmithKline and containing a particular immune boosting ingredient, was given to roughly 30 million people across Europe, including many children. And in the months and years that followed, doctors in several countries, especially in places like Finland and Sweden, noticed an alarming spike in new cases of childhood narcolepsy. The studies that followed found that children who had received that specific vaccine had a dramatically increased risk of developing narcolepsy. In one Finnish study, around 13 times the normal rate, with hundreds of cases eventually reported across Europe. The vaccine was restricted, and a different non-boosted formulation had been used in the United States, where this spike was not seen. As terrible as that was for the families involved, it served as a grim natural experiment that confirmed the autoimmune theory of narcolepsy. The best current understanding is that, in a small number of genetically vulnerable children, the immune response triggered by that vaccine, and likely by the swine flu infection itself, ended up cross-attacking and destroying their orexin neurons, switching off their stay-awake signal for life. There is no cure for narcolepsy yet, but it can be managed. People take stimulants during the day to fight the crushing sleepiness, and there is a powerful medication taken at night that helps with the cataplexy attacks. But the most hopeful frontier comes straight from understanding the cause. If narcolepsy is fundamentally a disease of missing orexin, then the obvious fix is to put the orexin signal back. Drug companies are now developing and testing medicines designed to do exactly that, to mimic orexin and switch the stay-awake signal back on, which could one day treat the actual root of the disease, rather than just papering over the symptoms. It is a direct payoff from those narcoleptic dogs and knockout mice, the long road from a strange collapsing dog to a drug aimed at the precise molecule it was missing. It was the worst possible way to prove a scientific point, that vaccine tragedy, an accidental demonstration that an immune reaction really can wipe out the exact cells whose loss causes narcolepsy. Hold on to that molecule, orexin, the stay awake chemical, because it is going to come back at the very end of this story in a completely unexpected and almost opposite way. Narcolepsy is the boundary between waking and sleep breaking down in one direction, with sleep crashing into waking. But the boundary can glitch in the other direction too, leaving people stuck in eerie in-between states. And these glitches, called parasomnias, are some of the strangest things the human brain does. The key to understanding most of them comes straight from what we already know about the sleep stages, in particular the fact that during deep non-REM sleep, your body is not paralyzed, while during REM it is. Take sleepwalking. People assume sleepwalkers are acting out a dream, but they are not, because dreams happen mostly in REM, where the body is paralyzed and cannot move at all. Sleepwalking actually happens during deep, slow wave sleep, usually early in the night, when the body is free to move, but the conscious mind is still switched off. What is happening is an incomplete arousal, where the part of the brain that controls movement wakes up while the part that handles awareness and judgment stays asleep. So the person can sit up, walk around, get dressed, even hold a clumsy conversation or drive a car, all while genuinely unconscious and remember none of it afterward. There are documented cases of people preparing food, leaving the house, and doing far more complex things while completely asleep because the body's controls came online while the mind never did. The same mechanism explains one of the most frightening things a parent can witness, the night terror, which is completely different from a nightmare, even though the names sound similar. A nightmare is a bad dream. It happens in REM, late in the night, and the person can usually remember it. A night terror is not a dream at all. It happens during deep non-REM sleep, usually in young children, and it looks horrifying. The child suddenly sits bolt upright, eyes wide open, screaming in apparent terror, sweating, heart pounding, completely inconsolable and unresponsive to comfort. And then, after a few minutes, it just stops. The child lies back down, and in the morning, they have no memory of it whatsoever. It is not fear of anything. It is a body half ripped out of its deepest sleep, with all the alarm systems firing while the dreaming, remembering, reasoning mind never woke up at all. For the parent, it is terrifying, but for the child, it is, in a sense, nothing, because no one was home to experience it. From there, the list of sleep oddities gets stranger and stranger. There is a harmless but bizarre experience called exploding head syndrome, where, as a person is drifting off to sleep, they hear a sudden, enormously loud noise inside their head, like a bomb going off, a gunshot, or a crash of cymbals, even though there is no sound at all and no pain. It seems to be a hiccup in the way the brain powers down its hearing systems as you fall asleep, and despite the alarming name, it does no harm, though it can scare people badly. There is restless legs syndrome, an almost unbearable creeping urge to move the legs that strikes at rest, especially at night, and can make falling asleep genuinely difficult. And there is a rare condition, sometimes nicknamed Sleeping Beauty Syndrome, where a person, usually a young man, falls into episodes of sleeping for the vast majority of the day for days or even weeks at a time, waking only briefly and behaving strangely when they do, before the episode lifts and they return to normal for months until the next one. All of these have the same underlying lesson. Sleep and waking are not a simple toggle, but a careful coordination of many different brain systems that are supposed to switch over together. When they fall out of step, when the body wakes while the mind sleeps, or the alarm fires while no one is conscious to feel it, or the dream paralysis arrives at the wrong moment, you get these uncanny states that sit between the two worlds. They are glimpses of just how much machinery is involved in something we take completely for granted. And they are still, in the end, sleep misbehaving rather than sleep failing. The true catastrophe, the thing that tells us what sleep is really worth, is what happens when you take it away entirely. So we know sleep does these essential jobs, and we know what it looks like when sleep breaks down piece by piece. But what about the most direct test of all? What actually happens to a healthy person who simply refuses to sleep for as long as they possibly can? A few people have tried to find out, and the results are some of the most revealing data in the entire field, because the way a deprived brain falls apart tells you exactly what sleep was holding together. One of the earliest and most disturbing cases was a New York radio host named Peter Tripp, who in 1959 decided to stay awake for 200 hours, more than 8 days, as a publicity stunt for charity, broadcasting his show the whole time from a glass booth set up in Times Square so the public could watch. The first couple of days he was fine. Then it began to come apart. He started having trouble with simple mental tasks. He became irritable and abusive. And then he started to hallucinate, seeing things that were not there, like spiders crawling out of his shoes and flames. Toward the end, he became genuinely paranoid and delusional, at one point reportedly becoming convinced that a doctor who had come to check on him was actually an undertaker, there to bury him, and trying to flee. By the time he finished, he had effectively been driven into a temporary psychosis by lack of sleep. He did recover after sleeping, but observers noted he never seemed quite the same. A few years later, in 1964, came the most famous case of all, and it was, of all things, a high school science fair project. A 17-year-old in San Diego named Randy Gardner set out to break the world record for staying awake, with two friends taking shifts to keep him up and log what happened. He used no stimulants at all, no pills, getting by on cold showers, loud music, the occasional Coca-Cola, and a lot of physical activity. As word got out, the Stanford sleep researcher William Dement, the same man who had helped discover the link between REM and dreaming a decade earlier, drove down to monitor him, along with a Navy medical officer. Gardner's decline followed a path that should sound familiar by now. By around the third or fourth day, he was nauseous, deeply foggy, and struggling to remember things, describing it later as feeling like an early Alzheimer's brought on by lack of sleep. He developed problems with concentration, mood swings, paranoia, and hallucinations, at one point apparently mistaking a street sign for a person. But there was a strange counterpoint that fascinated the researchers. Even badly sleep deprived, with Dement keeping him busy, Gardner could still rally for short stretches, and famously, during the experiment, he beat Dement at pinball game after game. His brain was clearly being shredded, and yet for brief moments he could still pull himself together. In the early hours of the 8th of January, 1964, Gardner officially broke the record, having stayed awake for 264 hours, which is 11 days. Then he finally went to sleep. And here is the part that genuinely surprised the scientists. He slept for only about 14 hours, woke up, and was more or less fine. He did not need to sleep for days on end to repay the 11-day debt. His brain prioritized plunging straight into extra deep sleep and extra REM to recover the most important parts first, and within a day or so he was back to normal. The body does not pay back lost sleep hour for hour. It triages, grabbing the most critical sleep first, which tells you something about what it values most. There is a sober footnote to both of these stories, though. Peter Tripp, the radio host, recovered from his sleepless psychosis, but people who knew him felt that something in him had shifted afterward, that the man who came out was not quite the man who went in. And Randy Gardner, the teenager who looked like the proof that you could bounce right back, reported decades later that he was tormented by terrible insomnia in his older years, and he came to wonder whether the stunt had done some lasting damage after all, whether or not those later problems were truly caused by that one extraordinary stretch. The lesson the scientists drew was clear enough. The fact that you can recover from a single brutal episode does not mean the episode was free. The body keeps a longer ledger than a single night of catch up sleep can settle. People kept pushing the record higher after that, sometimes well past 2 weeks, with the help of stimulants, with one documented attempt reaching over 18 days. But the danger became clear enough that the keepers of the world records eventually stopped recognizing attempts at staying awake at all. In the late 1990s, specifically because they did not want to encourage people to damage themselves chasing it. There is now officially no sanctioned record to break because the act of breaking it is considered too harmful. And there was a darker piece of evidence lurking in the animal research because you cannot ethically push a human all the way to the end. In a famous set of experiments, rats that were forced to stay awake completely with no sleep at all did not just get tired. After a couple of weeks, their bodies fell apart in strange ways. They lost the ability to regulate their temperature. Their bodies broke down despite eating more than usual, and they died. Total, prolonged sleep deprivation was not survivable for them. The lesson hanging over all of this human record chasing was that sleep is not optional in the way food can be skipped for a while. Push it far enough, and the body does not just suffer, it stops working. But you do not need anything as extreme as 11 sleepless days to wreck a brain. And this is the part that should worry the most people, because it applies to ordinary life. In carefully controlled studies, researchers have taken healthy people and simply limited them to around 6 hours of sleep a night for 2 weeks. By the end, those people were performing on attention and reaction tests about as badly as people who had been kept totally awake for 2 full days. But here is the genuinely alarming part. When you asked them how they felt, they reported only feeling a little bit off. They had no idea how badly they were actually functioning. That is the trap of chronic sleep loss. You adapt to the feeling of being tired long before you adapt to the impairment. So you end up severely degraded while sincerely believing you are basically fine. You become a bad judge of your own state, which means the people most impaired are often the most confident that they are handling it. Part of what is happening under the hood is something researchers call local sleep, where in a sleep-deprived brain that is technically awake, small patches of the brain briefly nod off into a sleep-like state on their own, flickering offline for a moment and then back. So a tired person can be sitting there with their eyes open, seemingly awake, while bits of their brain are essentially asleep, which is part of why exhausted people make sudden, baffling errors, missing something obvious right in front of them. And then there are full micro sleeps where the whole brain blinks out for 1 or 2 seconds without the person even realizing it happened. Sitting in a chair, a microsleep is nothing. Behind the wheel of a car at speed, 1 or 2 seconds with the brain offline is more than enough to drift into oncoming traffic. Which is why driving while badly sleep deprived has been measured as impairing you in ways genuinely comparable to driving drunk. And these failures do not stay in the laboratory. When investigators have dug into some of the worst disasters of the modern era, fatigue and sleep deprivation keep turning up as a contributing factor. The grounding of the Exxon Valdez oil tanker, one of the most destructive oil spills in history, happened with the crew operating on too little rest, the third mate reportedly having been awake for something like 18 hours. Investigations into the nuclear accident at 3 Mile Island, the catastrophe at Chernobyl, and the explosion of the space shuttle Challenger all pointed to sleep deprivation and exhausting shift schedules among the people making critical decisions as a factor in the chain of errors. And notice the eerie pattern in several of them. They unfolded in the small hours of the early morning, right in the deep circadian trough that Nathaniel Kleitman had identified decades earlier, the window when human alertness and judgment naturally bottom out. Kleitman's quiet little finding, that performance itself runs on a clock, was written in disaster reports the whole time, which brings us to the darkest and most important part of this entire story. Because for almost everyone, sleep deprivation has a built-in safety valve, which is that eventually your body forces you to sleep whether you want to or not. The pressure becomes overwhelming. You start having micro sleeps, tiny involuntary lapses where you blink out for a second or two, and finally you simply go under. You cannot truly stay awake forever because your biology will not let you. But there are people for whom that safety valve breaks. People whose brains, through no choice of their own, slowly and completely lose the ability to sleep and never get it back. And what happens to them is the single most powerful proof we have of just how essential sleep really is. There is a disease called fatal familial insomnia, and the name is exactly as literal as it sounds. It is a disease that runs in families, that starts with insomnia, and that is always, without exception, fatal. There is no treatment and no cure. And the way it kills is by taking sleep away from a person completely and never giving it back. Much of what doctors first learned about it came from a single family in the Venice region of Italy who carried this curse through their bloodline for something like 200 years. Generation after generation, otherwise healthy adults, usually somewhere around their 50s, would suddenly start to change. For a long time, the family did not even understand what was happening to them, and over the centuries, their relatives' deaths were written down as all sorts of other things: nervous exhaustion, encephalitis, even insanity, because nobody recognized the pattern or wanted to. In one telling, a generation might have over a dozen children, and half of them would die of this. The case that finally cracked it open was a man known publicly only as Silvano to protect the family. In the early 1980s, in his early 50s, Silvano began to show the signs. He started sweating heavily, his pupils shrank to pinpoints, his heart raced, and he could not sleep. At first, it was a worsening insomnia, but it kept progressing past anything that sleeping pills could touch toward a near total inability to sleep at all. Silvano knew exactly what was coming because he had watched relatives die of it, and he made the decision to have his decline studied and filmed at a university clinic so that science might finally understand the thing destroying his family. What the doctors documented was a slow, conscious descent. As the disease advanced, Silvano was trapped in a state that was neither true waking nor true sleep. His body would try to drift toward sleep and jerk back, unable to actually get there. He drifted through exhaustion, confusion, and waking dreams, his body breaking down from the strain of never resting, sliding toward a vacant, hollowed out stare. And then, like everyone in his family, after a span of months, he died. Silvano passed away in 1984, and he donated his body to science, which is part of how the disease was finally understood. When researchers examined the brains of Silvano and his relatives, they found the cause, and it is genuinely chilling. The damage was concentrated in a deep brain structure called the thalamus, which acts as a kind of central switchboard for the brain and is critically involved in regulating sleep. In the victims, the thalamus was riddled with tiny holes, eaten away until it looked almost like a sponge. And the thing eating it was not a virus or a bacterium. It was a prion, which is one of the strangest and most sinister agents in all of biology, a single misshapen protein. Here is what makes a prion so terrifying. Your body normally contains a particular protein folded into a specific healthy shape. In this disease, a tiny inherited mutation causes some of those proteins to fold into the wrong shape. And a misfolded prion has a horrible property, which is that when it touches a normal, correctly folded version of the same protein, it forces that one to misfold too, turning it into a copy of itself. So one bad protein makes two, two make four, and a chain reaction spreads through the brain, converting healthy protein into deadly misfolded protein, killing brain cells and leaving those sponge-like holes behind. It is the same family of disease as mad cow disease and the more famous human prion disease, and there is, to this day, no way to stop it. In fatal familial insomnia, the prion homes in on the thalamus, destroys the brain's ability to generate sleep, and the person simply cannot sleep their way out of the exhaustion that is killing them. Prions are worth pausing on because they break a rule we thought we understood. Almost everything that infects and spreads, a virus, a bacterium, a fungus, carries genetic material, the molecular instructions for copying itself. A prion has none. It is just a protein in the wrong shape, and it spreads its damage purely by touch, by physically forcing other proteins to deform the same way, a chain reaction of misfolding with no genes involved at all. That is why this family of diseases shocked scientists so deeply, and why the discovery of how prions work earned a Nobel Prize. The same kind of agent causes mad cow disease in cattle and its human form, and it caused a haunting illness once found in a community in Papua New Guinea that was spread through funeral rituals, all of them leaving the same sponge, like coals in the brain, all of them untreatable. And here is a detail that makes fatal insomnia even more unsettling. While the famous Italian family inherits the mutation, there is also an even rarer version that strikes people with no family history at all, where the protein simply misfolds spontaneously by terrible chance in someone whose genes were perfectly normal. It is vanishingly rare, but it means that, in principle, this could begin in a person who had no warning written into their family tree, no reason to ever suspect it was coming. The machinery that lets you sleep can, in the rarest of cases, simply turn on itself. And this is the brutal heart of the whole story we have been building. Strip everything else away, and here is a disease whose entire mechanism is the removal of sleep, and the result is not just tiredness, it is delirium, physical collapse, and reliable death within months to a couple of years. All the theories we walked through, the memory filing, the brainwashing itself, the body repair, the emotional processing, none of it can happen if the brain physically cannot enter sleep. Fatal familial insomnia is, in the cruelest way imaginable, the final proof that sleep is not a luxury or a habit or wasted time. It is load bearing. Take it away entirely, and a human being dies. But the story does not end in pure darkness, and this is where it turns. In 2010, a young woman named Sonia Valab, who was in her second year at Harvard Law School and busy planning her wedding, watched her mother die of a mysterious, rapidly progressing illness that doctors could not name. Afterward, the cause was identified. It was fatal familial insomnia, and that meant Sonia had a 50-50 chance of carrying the same mutation. She chose to get tested, and the test came back positive. She had the gene. Barring a breakthrough, the same disease that took her mother was, in all likelihood, waiting for her, probably decades away, but coming. Most people would not know what to do with that. What Sonia and her husband, Eric Minikel, did was extraordinary. Neither of them was a biologist. She was a lawyer. He was a transportation analyst. So they quit their careers, went back to school, taught themselves the science from the ground up, sitting in on classes and earning the credentials, and turned themselves into working scientists, eventually running a research program dedicated to a single goal: finding a way to stop prion disease before it can start, in time to save Sonia and everyone else who carries one of these mutations. She is, in the most literal sense possible, a scientist racing against her own genes, trying to cure the disease written inside her before it wakes up. There is no guarantee she will win that race. But the fact that the deepest, darkest corner of sleep science, a 200-year-old family curse that kills by stealing sleep, has produced one of the most determined searches for a cure in modern medicine, is about as fitting an ending as this subject could ask for. The thing that takes sleep away has become the thing driving someone to fight hardest to understand it. If you want a sense of how non-negotiable sleep really is, look at the lengths the rest of the animal kingdom goes to in order to get it, even when sleeping should be impossible or suicidal. Because here is the thing: sleep is so essential that animals which absolutely cannot afford to switch their whole brain off have evolved jaw dropping workarounds rather than skip it. Take dolphins. A dolphin has a problem, which is that it has to consciously decide to surface and breathe. So if it ever fully lost consciousness the way you do, it would stop breathing and drown. It cannot just switch off. So dolphins, along with other whales, some seals, and a number of birds, evolved something called unihemispheric sleep, which means they sleep with only one half of their brain at a time. One hemisphere goes into deep, slow wave sleep, while the other stays awake to keep them breathing, keep them swimming, and keep one eye open, watching for danger. After a few hours, they swap, the rested half taking over, while the other half finally sleeps. They are, in a sense, always half asleep and half awake, and they may never experience true REM sleep at all because the paralysis would sink them. And then there are birds that have taken this even further. The great frigate bird soars over the open ocean for weeks at a time without ever landing, and for a long time it was a mystery how it could possibly sleep on a journey like that. The answer, when researchers finally tracked it, was almost unbelievable. The birds sleep while flying in tiny bursts of a few seconds, sometimes shutting down half the brain at a time, and sometimes briefly both halves, all while soaring on the wind. Over a full day of flying, one of these birds might get a grand total of around 45 minutes of sleep in scraps of seconds, and that is apparently enough to keep it going. The fact that even a bird crossing an ocean refuses to simply skip sleep and instead grabs it in 12-second pieces mid flight tells you how deep the need runs. The variety across the animal kingdom is enormous. A giraffe gets by on something like 2 hours of sleep a day, often in short bursts while standing, presumably because lying down on the open savanna is a good way to get eaten. A brown bat, at the other extreme, sleeps around 20 hours a day. Big cats and many other predators sleep most of the day too, because they can afford to. The platypus, of all creatures, has been found to have more REM sleep than almost any other animal. And newborn dolphins and orcas appear to barely sleep at all for the first month or so of life, with their mothers staying awake right alongside them, which seems to contradict everything until you realize the calves are too vulnerable to be unconscious near the surface. Across all of it, from the bat hanging in a cave to the bird napping in flight, the pattern is the same. Sleep gets bent, split, shortened, and reshaped, but it almost never gets skipped. It even goes all the way down to the fruit flies that helped us crack the clock genes. Fruit flies sleep in the sense that they have long periods of stillness and reduced responsiveness. They rest at predictable times of day, and if you keep a fruit fly awake, it gets impaired and then has to make up the lost rest afterward, exactly like a sleep deprived person. Insects, fish, worms, Every branch of the animal tree that has been carefully checked shows something that functions like sleep. And then there is the finding that pushes the whole thing past the point of comfort, which involves the jellyfish. In a much discussed experiment, researchers studied a kind of jellyfish and found that at night it enters a clear sleep-like state, pulsing far less, becoming slower to respond to the world around it, and, most tellingly, needing to make up rest afterward if it was kept active when it should have been resting. The reason this matters so much is that a jellyfish does not have a brain. It has no central nervous system at all, just a loose, diffuse net of nerves spread through its body, and yet it sleeps. That single fact suggests something profound, that sleep is older than the brain itself, that the need to power down and recover is built into the most basic wiring of animal life, present before nature ever invented a mind to switch off. On the opposite end, wild elephants have been found to sleep only around 2 hours a day, the least of any mammal yet measured, often standing up and sometimes going a full day or two without sleeping at all while on the move. But even they cannot skip it forever. They take the least they can get away with, and then they take it. And that universality is in itself one of the strongest arguments for how important sleep is. If sleep were just an idle habit, you would expect at least some animals somewhere to have evolved their way out of it entirely, especially the ones for whom being unconscious is so dangerous. Instead, evolution kept it everywhere, from the brainless jellyfish to the bird crossing an ocean. And in the animals that could not afford the normal version, it engineered elaborate, costly workarounds to preserve it. Nature treats sleep as a requirement, not a preference, which makes the next group of people all the more remarkable, because they are the closest thing that exists to an exception. Almost everyone who claims they only need 4 or 5 hours of sleep is wrong. They are not short sleepers. They are sleep-deprived people who have simply gotten used to functioning at a reduced level, the way you can get used to a dim room until you forget what bright looks like. The research is brutally clear that the large majority of adults need somewhere in the range of 7 to 9 hours, and that the people who insist they thrive on 5 are usually just unaware of how much sharper they would be with more. But, and this is the fascinating exception, a tiny number of people genuinely are different. They really can run on 4 to 6 hours, night after night, feeling fully rested with no apparent ill effects, and it is written into their genes. The scientist who has done the most to track these people down is a geneticist named Yinghui Fu. In 2009, her team studied a mother and daughter who were natural short sleepers, going to bed at a normal time but waking up genuinely refreshed after around 6 hours, and found that they carried a particular mutation in a gene called DEC2. These were not people who had trained themselves to wake early. They were born that way, and the trait ran in the family. Then, after a decade more of work, in 2019, her team found a second short sleep gene in a different family who did not have the first mutation. This one in a gene called ADRB1. And over the following years, they kept finding more, building up a small collection of rare genetic variants that all seem to let a person do, in a handful of hours, whatever sleep is supposed to accomplish. And here is the beautiful connection that ties this all the way back to the narcolepsy story. Remember orexin, the stay awake chemical, the one whose loss causes narcolepsy. It turns out that one of the things the DEC2 gene normally does is help control orexin levels, and the short sleep mutation appears to nudge orexin production up, so these people make a bit more of the stay awake signal, build brains that are a little easier to keep awake and rouse, and seem to get their sleep's work done more efficiently in less time. So the same molecule sits at both extremes. Lose your orexin neurons, and you have narcolepsy, unable to hold yourself awake. Get a rare tweak that bumps your orexin up, and you may be one of the lucky few who can run a full life on 5 hours. The stay awake chemical is the dial, and almost all of us are set somewhere in the ordinary middle. The crucial point, though, is how rare these mutations are. We are talking about the sliver of the population. For everyone else, and that means almost certainly you, trying to live like a natural short sleeper does not turn you into one. It just turns you into a chronically sleep-deprived person carrying a growing debt with all the costs that come with it: the foggy memory, the worse mood, the weakened immune system, the uncleared waste in the brain, the long-term risks to the heart and the mind. The short sleepers are not a goal to aim for. They are a genetic accident and a reminder that your own sleep need is set largely by biology you did not choose, not by willpower. So how much sleep does a normal person actually need? The broad consensus from the research is that most adults need somewhere between 7 and 9 hours a night to function at their best, with the true need set by your individual biology somewhere in that band. Children and teenagers need considerably more, and there is an important wrinkle there that schools mostly ignore. Around puberty, the body clock naturally shifts later, so teenagers are biologically wired to fall asleep late and wake late, which means dragging a 16-year-old out of bed for a 7 in the morning class is fighting their physiology, not their character. They are not lazy, their clock has genuinely moved, and the early start is asking them to perform in the middle of their biological night. But here is something that should make you question one of your deepest assumptions about sleep. We treat 8 hours in a single, unbroken block as the natural, obvious, correct way to sleep. It may not be. A historian named Roger Eckertz spent years digging through old diaries, court records, medical books, and literature from before the industrial age, and he found something remarkable hiding in plain sight in the language of the past. People used to refer completely casually, as if everyone understood it, to their first sleep and their second sleep. What the records describe is that before artificial lighting, many people in the Western world slept in 2 chunks. They would go to bed not long after dark, sleep for a few hours, then wake naturally in the middle of the night for an hour or two, a quiet, wakeful window in which people prayed, reflected, tended the fire, talked with whoever was beside them, or even got up and visited neighbors before going back down for their second sleep until morning. This was not insomnia, it was not a problem. It was simply how a night was shaped, and it appears across a huge number of old sources without anyone bothering to explain it, because everyone already knew. The single consolidated block of sleep we now consider normal may be a fairly recent invention, manufactured by a world of artificial light and rigid work schedules that compressed the night, because that is the other half of the story. Electric light changed human sleep more than almost anything in our history. For all the millennia before it, when the sun went down, the options for activity collapsed, and people slept earlier and longer and more in tune with the dark. The light bulb, and then the glowing screens that followed it, pushed our bedtimes later and later, tricking the very clock we talked about into thinking the day was not over. Studies of communities that still live without electricity find that they tend to go to sleep earlier and live more closely tied to the natural light cycle than the rest of us, who stay up bathed in artificial brightness. Across the last century or so, as a species, we have quietly trimmed our nightly sleep and shoved it later, and we are running the largest uncontrolled experiment in sleep deprivation in human history without ever having agreed to it. There is also the matter of the nap, which much of the world has always understood better than the modern office does. The midday rest, the siesta, lines up neatly with that biological afternoon dip in alertness that Kleitman measured, the natural low point that hits in the early afternoon regardless of lunch. Splitting sleep across a long night and a short midday nap is a perfectly natural human pattern, and the idea that all sleep must happen in one nighttime block and that wanting to rest in the afternoon is a weakness is, again, more a product of industrial scheduling than of biology, and sleep keeps changing across your whole life. As people get older, their sleep tends to get lighter and more broken, and crucially, they get less of the deep, slow wave sleep, the very stage that does so much of the body repair, the memory filing, and the brain cleaning we have talked about. That is a big part of why many older adults wake more during the night and feel less restored by it. And it sets up a quietly frightening loop tied straight back to that brainwashing system. Poorer sleep in later life means less of the deep sleep that clears waste like beta amyloid out of the brain, which can let more of it build up, and the diseases that build up drives then damage the very brain regions that generate deep sleep, degrading the sleep further still. Bad sleep and brain decline in old age are not just correlated, they appear to actively feed each other, each making the other worse. By this point, you might be lying there wondering what you are actually supposed to do with all of this, especially if you are someone who struggles to sleep well. So, before we close, here is what the science actually points to, stripped of the gadgets and the gimmicks, because the things that genuinely work are mostly free and mostly about cooperating with the systems we have spent this whole story describing rather than fighting them. The single most powerful lever is consistency, and it is the one almost nobody wants to hear. Going to bed, and especially waking up at roughly the same time every day, including weekends, is the most effective thing most people can do because it is exactly what your circadian clock is begging for. The clock thrives on a steady signal and falls apart when you yank it around, sleeping in for hours on Saturday and then forcing yourself up early on Monday, which, as we saw, is just self inflicted jet lag. A regular wake time is the anchor that holds the entire rhythm steady, and your wake time matters even more than your bedtime because it is the morning that sets the clock for the day to come. After that, it is all about light and temperature, the two signals the system reads most strongly. Get bright light, ideally real sunlight, into your eyes early in the day, because that is what tells your master clock the day has begun and starts the countdown toward sleepiness that night. Then, in the evening, do the opposite. Dim the lights and get off the bright screens as bedtime approaches, so that the rising darkness lets your melatonin climb on schedule instead of being held back by a glowing phone an inch from your face. And keep your bedroom cool because your core body temperature actually has to drop by about a degree for you to fall and stay asleep, which is also why a warm bath or shower an hour or so before bed can help, since pulling heat out to your skin lets your core cool down faster afterward. Then there are the obvious chemical culprits we already met. Cut off caffeine in the early afternoon, remembering that it lingers for many hours and that you may be one of the slow metabolizers still feeling a lunchtime coffee at midnight. And stop using alcohol as a sleep aid because while it knocks you out faster, it shreds the quality of the night that follows. Both of those are working directly against the adenosine and the sleep stages we walked through earlier. The last piece is the most counterintuitive, and it matters most for people who lie awake frustrated. Sleep is one of the only things in life that actively runs away from you the harder you chase it, because the anxiety of trying to fall asleep is itself a wakeful, alert state, the exact opposite of what you need. So the advice that works is almost paradoxical, which is to stop trying. Keep the bed as a place for sleep, not a place where you lie there scrolling and worrying. And if you find yourself wide awake and frustrated, get up, go do something calm and boring in dim light, and come back only when you actually feel sleepy. So your brain keeps learning that the bed means sleep rather than means lying there fighting. That simple retraining is the heart of the most effective long-term treatment there is for chronic insomnia, a structured approach that, over time, beats sleeping pills, and it works precisely because it stops the person from battling their own sleep system and lets the machinery we have described do what it already knows how to do. So put it all together. For most of human history, we thought sleep was nothing, an empty switching off of a brain with nothing better to do. We now know it is one of the most active and important things your body ever does. It is when your memories get filed into permanent storage and woven into what you already know. It is when your brain physically washes its own waste out, including the gunk tied to dementia. It is when your body repairs itself and your immune system does its work and your emotions get processed down to a manageable size. It runs on a clock built out of self-silencing genes and set each day by light, and on a pressure that builds out of a single molecule, and that you spend your mornings fighting with coffee. And take it away completely, and a person dies. That is not nothing. That is arguably the most important thing you do. And yet, we are, as a species, terrible at it right now. We built a world of artificial light, glowing screens, late shifts, early alarms, and round-the-clock noise, and then we wedged sleep into whatever gap was left over, treating it as the first thing to sacrifice whenever life gets busy. A huge fraction of adults are running a chronic sleep debt and have no idea because, like the fake short sleepers, they have forgotten what being fully rested even feels like. The costs of that show up in places people rarely connect back to sleep. Drowsy driving, for instance, impairs you in ways genuinely comparable to drunk driving, slowing your reactions and wrecking your judgment, and it kills people on the roads every year. You can even see it in the calendar. There is a long-running debate about the twice-yearly clock change for daylight saving time, and a number of studies linked the spring change, where everyone loses an hour of sleep, to a measurable bump in problems in the days right after. One often cited study found heart attacks rising by around a quarter on the Monday after the spring clock change, and others have reported small spikes in strokes and in fatal car crashes in that same window, with the telling detail that the autumn change, when people gain an hour of sleep, tends to show the opposite, a small dip. It is worth being honest that the science here is contested, because a recent very large study found no significant rise in heart attacks around the clock change at all, which suggests the earlier, smaller studies may have overstated the effect. But even setting the heart attack question aside, the crash data has pointed the same direction for years, that yanking an hour of sleep away from an entire population at once leaves more tired, slower, more dangerous people on the road the next morning. A single hour, multiplied across millions of people, is enough to show up in the statistics, which tells you how thin the margin already is. And in the long run, the chronic version is the one that matters most. Years and decades of cutting sleep short are linked again and again to higher rates of heart disease, of obesity and diabetes, of weakened immunity, of depression and anxiety, and through that waste clearance system we talked about, to a raised risk of the kind of brain decline that ends in dementia. None of this is about one bad night which you can recover from, the way Randy Gardner bounced back after 14 hours. It is about the slow accumulation, the night after night after night of skimming sleep off the top, the debt that never quite gets paid and quietly compounds. Here is what makes all of this almost funny in a bleak way. The single most powerful, most universally agreed upon piece of health advice in all of medicine, the thing that helps your memory, your mood, your weight, your heart, your immune system, your brain's long-term health, and your daily performance all at once, is also completely free, available to everyone, and requires no equipment, no subscription, and no effort beyond lying down and letting it happen. And it is the one piece of advice almost nobody actually follows. We will spend money on supplements and gadgets and routines, chasing a fraction of what a consistent full night of sleep would give us for nothing. Think back to where this started, to Eugene Aserinsky sitting in a dark lab in 1951, broke and exhausted, watching ink pens scratch back and forth across a roll of paper, refusing to believe his machine was broken. He had stumbled onto the fact that the sleeping brain, far from being switched off, was as busy as a waking one, running its own hidden schedule every single night. Everything we now know, the cycles, the clock, the cleaning, the memory filing, the dreams, the disorders, all of it flowed out of that one stubborn refusal to look away. You are going to spend somewhere around 26 years of your life asleep. For almost all of human history, that looked like 26 years of nothing, a long dark blank in the middle of being alive. It turns out it is the opposite. It is 26 years of your brain and body doing the quiet, essential work that makes the other 50 something years possible at all. So, the best thing you can do, knowing all of this, is the simplest thing there is. Tonight, when the pressure builds and your clock says it is time, do not fight it. Turn off the light, lie down, and let your brain get to work. You have got a lot to do tonight, even if you will not remember a second of it.